Right now, on Venus, the sun rises in the west and sets in the east. Time runs backwards there. A single day on that planet, the time it takes to complete one rotation on its axis, lasts 243 Earth days. Its year, the time required to orbit the sun, takes only 225 Earth days. The planet completes an entire journey around our star before it finishes turning once on itself. This violates every intuition we have about how worlds should work. Yet Venus spins this way, locked in a rotation so slow and backwards that it rewrites the rules of planetary motion. The wrongness of Venus revealed itself gradually. In 1667, Giovanni Cassini observed Venus through his telescope in Bologna and attempted to measure markings on its cloud tops. He concluded the planet rotated once every 23 hours, roughly matching Earth. For nearly 3 centuries, astronomers accepted this estimate. They assumed Venus behaved like other planets, spinning forward in the same direction it orbited, completing its day in a reasonable time frame. The assumptions seemed safe. Mercury spins forward. Earth spins forward. Mars, Jupiter, Saturn, all the visible planets rotate in the same direction they orbit the Sun. Venus should follow the pattern. It does not. In 1962, radar observations from Earth penetrated Venus's thick clouds for the first time. Scientists at MIT's Lincoln Laboratory and the Jet Propulsion Laboratory bounced radio waves off the hidden surface and measured the Doppler shift in the returning signal. The data showed something impossible. Venus rotated backwards opposite to its orbital motion in what astronomers call retrograde rotation. The measurements also revealed the rotation period, 243.025 Earth days. The number seemed wrong. Researchers checked their equipment. They repeated the observations. The results held. Venus spins the wrong way, and it spins so slowly that its day exceeds its year. This should not happen. When the solar system formed 4.6 billion years ago, a rotating disk of gas and dust collapsed into the sun and planets. Everything inherited the disk's rotation. All the planets should orbit the sun in the same direction, and all should rotate on their axes in that same direction. The conservation of angular momentum, one of physics's most fundamental laws, demands it. You cannot easily reverse the spin of an entire planet. The energy required to stop Venus's forward rotation, then accelerate it backwards to its current state, exceeds the kinetic energy of all humanity's nuclear weapons by orders of magnitude multiplied by millions. Something catastrophic must have happened. The verification process took decades. Between 1962 and the early 1970s, radar telescopes at Arecibo in Puerto Rico, Goldstone in California, and Haystack in Massachusetts repeatedly measured Venus's rotation. The data converged on the same retrograde period. Then spacecraft arrived. NASA's Mariner missions in the 1960s and 70s, followed by the Pioneer Venus orbiter in 1978, mapped the planet's surface through radar. They tracked fixed landmarks over time and confirmed the ground truth. Venus rotates backwards with a period of 243.025 days. Its orbit around the Sun takes 224.7 Earth days. The orbital period is shorter. The year is briefer than the day. Think about that for a moment. If you stood on Venus's surface, assuming you could survive the 900 degrees Fahrenheit temperature and 92 times Earth's atmospheric pressure, you would watch the sun creep backwards across the sky. It would rise in the west. It would take 58.4 Earth days to travel from western horizon to eastern horizon to western horizon again, because one solar day on Venus, the time from sunrise to sunrise, equals 116.75 Earth days. That number derives from the complex interaction between Venus's backwards rotation and its forward orbit. The planet spins so slowly backwards that its movement around the Sun actually dominates the apparent motion of the Sun in Venus's sky. During one Venus year, the Sun rises and sets exactly twice. The statistical improbability weighs heavily on planetary scientists. Of the 8 planets in our solar system, only Venus rotates retrograde. Mercury rotates forward with a period of 58.6 days. Earth completes its rotation in 24 hours. Mars takes 24.6 hours. The gas giants spin even faster. Jupiter rotates in less than 10 hours. Saturn takes 10.7 hours. Uranus rotates in 17.2 hours, though its axis tilts 98 degrees, making it spin on its side. Neptune spins in 16.1 hours. Venus stands alone. Its rotation is backwards and slower than any other planet by a factor of 10. Astronomers examined 3 main hypotheses to explain this anomaly. The first proposed that Venus formed with retrograde rotation, somehow inheriting backwards angular momentum from local conditions in the protoplanetary disk. Computer simulations of planet formation show this scenario is possible, but extraordinarily unlikely. The disk's overwhelming rotation would have to be overcome by very specific, localized turbulence. The second hypothesis suggested that gravitational interactions with the Sun created a tidal bulge in Venus's thick atmosphere, which gradually slowed and then reversed the planet's rotation over billions of years. The mathematics showed this mechanism could work, but the timescales stretched credibility. The third hypothesis, now widely accepted, points to a massive collision early in Venus's history. The impact hypothesis proposes that Venus originally rotated forward like other planets, with a day lasting perhaps 10 to 20 hours. Then, approximately 4 billion years ago, during the late heavy bombardment when the inner solar system swarmed with planet-sized objects, a body roughly the size of Mars struck Venus at an oblique angle. The collision transferred enough angular momentum to reverse Venus's spin. Computer simulations run by planetary scientists at the Southwest Research Institute and NASA's Ames Research Center show that such an impact could flip Venus's rotation without destroying the planet entirely. The impactor would have vaporized. Venus would have melted. The planet would have taken millions of years to cool and solidify. But it would have survived, spinning backwards. The evidence supporting the impact hypothesis comes from multiple sources. Venus's extraordinarily slow rotation suggests a massive disruption. A glancing collision could impart retrograde rotation while preserving the planet's orbital parameters. Venus's lack of a moon, unlike Earth, which retained one from its own giant impact, fits the scenario. The impactor that hit Venus may have struck at such an angle that the debris either fell back to the planet or escaped Venus's gravity entirely. Additionally, Venus's surface shows no features older than 500 million years. The entire planet appears to have been resurfaced through volcanic activity relatively recently in geological terms. This could connect to internal heat and dynamics resulting from that ancient collision. But here is where it gets uncomfortable. The impact that reversed Venus's rotation should have left other signatures. Planetary scientists expected to find variations in Venus's gravity field or asymmetries in its internal structure. The Magellan spacecraft, which orbited Venus from 1990 to 1994, mapped the planet's gravity in exquisite detail. The measurements revealed Venus is remarkably symmetric. Its core, mantle, and crust show no obvious signs of a massive impact. The planet appears to have thoroughly mixed and equilibrated over billions of years. This makes sense given the intense heat and pressure, but it also erases the very evidence we need to confirm the impact hypothesis definitively. The consequences of Venus's backwards rotation extend beyond mere curiosity. The planet's slow spin affects its magnetic field, or rather, its lack of one. Earth generates a powerful magnetic field through the dynamo effect. Our planet's liquid iron outer core rotates rapidly, creating electric currents that produce magnetism. Venus has a similar iron core, likely partially liquid. But Venus rotates far too slowly for the dynamo mechanism to operate effectively. Without a magnetic field, Venus's atmosphere faces the solar wind directly. Charged particles from the Sun strip away atmospheric gases over time. Venus has lost most of its water this way. What was once potentially an ocean world became a hellish desert. The absence of a magnetic field also means Venus lacks protection from cosmic radiation. Any life that might have emerged on young Venus would have faced intense radiation from space. The thick carbon dioxide atmosphere provides some shielding, but not enough to create a habitable surface environment. Venus's backwards slow rotation thus connects directly to its inability to support life. The same collision that flipped the planet's spin may have sealed its fate as a lifeless world. Before you drift off, leave a comment. What time is it where you are right now, and where in the world are you watching from? The rotation affects Venus's atmospheric dynamics in profound ways. On Earth, the Coriolis effect, driven by our planet's rotation, creates the trade winds and jet streams that distribute heat around the globe. Venus rotates so slowly that the Coriolis effect is negligible at the surface. Instead, the atmosphere exhibits superrotation. The entire atmosphere rotates around the planet once every 4 Earth days, 60 times faster than the solid planet below. Winds at cloud level reach 350 kilometers per hour. Scientists still debate what drives this superrotation. The leading theory involves solar heating creating atmospheric waves that transfer momentum to higher altitudes, accelerating the winds. But the mechanism requires Venus's slow rotation to work. A faster spinning Venus would generate different atmospheric patterns entirely. The measurements of Venus's rotation period have grown increasingly precise over decades. Early radar observations in the 1960s carried uncertainties of several hours. By the 1980s, measurements narrowed to within minutes. Modern observations, combining radar data with tracking of surface features by orbiting spacecraft, pin Venus's sidereal rotation period, the time to complete one rotation relative to the stars, to 243.025 days, with an uncertainty of less than 1 day. Scientists have also discovered that Venus's rotation rate varies slightly. The planet's spin speeds up and slows down by several minutes over periods of years to decades. This variation likely results from exchanges of angular momentum between the solid planet and its massive atmosphere. Strong winds can push against mountains and alter the planet's rotation speed slightly, just as Earth's rotation slows by milliseconds during El Niño events when atmospheric patterns shift. The implications ripple outward. If a collision could reverse Venus's rotation, similar events likely occurred throughout the solar system. Uranus's extreme axial tilt probably resulted from one or more giant impacts. Earth's moon formed from a collision with a Mars-sized object called Theia. Mercury's outsized iron core may reflect a massive impact that stripped away much of its rocky mantle. The early solar system was violent. Planets crashed into each other. The survivors bear the scars. Venus's backwards rotation is one such scar, written in the planet's motion for billions of years. This raises uncomfortable questions about planetary habitability. Venus orbits in what astronomers call the circumstellar habitable zone, the region around a star where liquid water could exist on a planet's surface. Venus receives about twice the sunlight Earth does, but that alone need not preclude oceans. A planet with different clouds, a different atmosphere, or a different rotation might remain habitable despite Venus's orbital distance. But Venus's actual rotation, combined with its thick carbon dioxide atmosphere and runaway greenhouse effect, created hell. If the giant impact had not occurred, if Venus still spun forward with a day of 10 or 20 hours, the planet might have retained its water. It might have developed a magnetic field. It might have remained habitable. The collision that reversed Venus's spin may have destroyed the possibility of life on the planet closest to Earth. Human missions to Venus must contend with this reality. The planet's slow rotation means that any location on the surface experiences 58 Earth days of continuous sunlight, followed by 58 days of darkness. Solar panels become impractical. Temperature variations between day and night are smaller than expected because the thick atmosphere distributes heat efficiently, but the extreme length of the day-night cycle creates unique engineering challenges. Proposed missions involve balloons floating in Venus's upper atmosphere, where temperatures and pressures resemble Earth's surface conditions. But even there, the backwards rotation creates unusual wind patterns that mission planners must account for. The physics of Venus's rotation connects to fundamental questions about angular momentum in isolated systems. The solar system is not perfectly isolated. The sun's tidal forces gradually slow planetary rotations. The moon's gravity slows Earth's rotation by about 2 milliseconds per century, lengthening our day. But these effects act over billions of years. Venus's backwards rotation cannot result from tidal forces alone. The reversal required a sudden, violent input of energy and momentum. This tells us that planets are not gentle spheres spinning peacefully in space. They are survivors of cosmic collisions, bearing the histories of catastrophic impacts in their motions. Understanding Venus's rotation also refines our search for habitable exoplanets. Astronomers have discovered thousands of planets orbiting other stars. Many orbit close to their stars, in what would be Venus-like conditions in our solar system. The rotation of these exoplanets matters. A planet tidally locked to its star, always showing the same face like the moon does to Earth, experiences permanent day on one side and permanent night on the other. Extreme temperature differences make such worlds less likely to support life. A planet with normal rotation distributes sunlight and heat more evenly. But a planet with Venus-like rotation, spinning slowly backwards, occupies an intermediate state. Its habitability depends on complex interactions between rotation, atmosphere, and stellar radiation. Detecting the rotation of exoplanets requires advanced techniques that astronomers are only now developing. Venus serves as the test case. The story of Venus's rotation is the story of violence shaping worlds. The violence required to flip a planet's rotation operates at scales that defy human comprehension. Angular moment ehension. Angular momentum is conserved in the universe. This is not a suggestion or a tendency. This is one of physics's iron laws, as fundamental as the conservation of energy. When an object spins, it continues spinning unless an external force acts upon it. For a planet, that external force must equal the planet's entire rotational energy, then exceed it, then reverse it. Venus has a mass of 4.867 times 10 to the 24th kilograms. Before any hypothetical collision, it rotated with a period we estimate at 15 to 20 hours, based on models of planetary formation. To stop that rotation and reverse it requires transferring angular momentum on the order of 10 to the 35th kilogram meters squared per second. That number is meaningless until you understand what it represents in physical terms. Picture Earth's moon. Now imagine accelerating it to 10% the speed of light and slamming it into Venus. The kinetic energy approaches what would be needed. The impactor that struck Venus 4 billion years ago carried this much momentum and energy. It was not a small asteroid or a glancing blow from a comet. Current models suggest an object between the size of Mercury and Mars, perhaps 3,000 to 5,000 kilometers in diameter, struck Venus at an angle between 20 and 45 degrees from vertical. The impact velocity likely reached 20 to 30 kilometers per second, typical for objects in the inner solar system during the late heavy bombardment. At those speeds, matter behaves less like solid material and more like fluid. Rock vaporizes on contact. Shock waves propagate through planetary interiors at supersonic velocities. The entire planet rings like a bell. The collision physics works like this. The impactor approaches Venus with its own angular momentum, spinning and moving through space. Venus, rotating forward in the same direction it orbits, presents a moving target. The impactor strikes the surface at an oblique angle, not head-on. This is critical. A direct impact would destroy both bodies, creating a debris field that might coalesce into a new planet or scatter into space. An oblique impact transfers momentum more efficiently. Think of a pool ball striking another at an angle. The struck ball does not move in the same direction as the cue ball traveled. It moves at an angle determined by the impact geometry, conservation of momentum, and friction between the surfaces. Planets colliding in space follow the same principles, scaled to planetary masses. The energy released in such an impact exceeds the energy that would be released if every nuclear weapon on Earth detonated simultaneously by a factor of several billion. The impact site on Venus would have instantly vaporized, creating a cavity thousands of kilometers across. The shockwave would have propagated through Venus's mantle within minutes, potentially reaching the core mantle boundary on the opposite side of the planet within an hour. Rock heated to tens of thousands of degrees Kelvin would have been ejected into space at velocities exceeding Venus's escape velocity of 10.4 kilometers per second. Some of this material would have escaped Venus entirely. Some would have orbited briefly before raining back down. The planet's surface would have become a global magma ocean, with depths potentially reaching hundreds of kilometers. But here is where conventional understanding fails. Simple collision models that treat Venus and the impactor as rigid bodies predict that such an impact should do more than reverse the planet's rotation. It should shatter Venus entirely. The gravitational binding energy of Venus, the energy holding the planet together against its own gravity, is about 2 times 10 to the 32 joules. An impact energetic enough to reverse the rotation delivers roughly this much energy. The planet should disintegrate into fragments. It does not. Venus survived. This means the collision must have occurred in a very specific way, with the impact energy distributed throughout the planet's volume rather than concentrated at the impact site. The impactor must have been large enough and struck at a shallow enough angle that it effectively merged with Venus rather than exploding on contact. Computer simulations run at NASA's Ames Research Center and the Southwest Research Institute model this process using smoothed particle hydrodynamics. The technique treats the planet and impactor as collections of millions of particles, each representing a chunk of rock or iron hundreds of kilometers across. The simulation calculates gravitational forces, pressure, temperature, and momentum for each particle at every time step. A typical simulation might model the first 24 hours after impact, computing particle interactions billions of times. The results show that an impactor roughly the size of Mars, striking at 30 degrees from vertical at 25 kilometers per second, can reverse Venus's rotation while keeping the planet intact. The impactor's iron core merges with Venus's core. The rocky mantles mix and flow. Material ejected into space amounts to only a few % of the combined mass. Most of the planet survives. The physics governing this outcome relies on how materials behave under extreme pressure and temperature. At the pressures in Venus's mantle, measured in gigapascals, rock does not shatter like glass. It flows like honey, albeit very stiff honey. The timescale matters. A sudden impact creates pressures that propagate as shock waves, potentially fracturing material. But if the impactor is large enough, comparable to the target planet, the collision becomes less like a bullet hitting a wall and more like two drops of water merging. The process takes hours, not milliseconds. The mantles have time to deform and flow rather than shatter. This is why only impactors above a certain size threshold can reverse a planet's rotation without destroying it. Smaller impactors create craters, larger ones merge. Here is an analogy that captures the essence. Imagine two spinning tops on a table, one spinning clockwise and one counterclockwise. Now imagine they are made of soft clay and you press them together while they spin. The clay mixes. The combined object spins in a direction determined by the angular momentum each top brought to the collision. If the counterclockwise top was larger and spinning faster, the merged blob might spin counterclockwise despite incorporating the clockwise top. Venus and its impactor merged this way. The impactor brought enough backwards angular momentum to overwhelm Venus's forward rotation. The result is a planet spinning retrograde. The measurable effects of this ancient collision persist today in subtle ways. Venus's moment of inertia, a measure of how mass is distributed within the planet, provides clues. If Venus were perfectly uniform, a sphere of constant density throughout, its moment of inertia would equal 0.4 times its mass, times the square of its radius. Measurements from spacecraft tracking data show Venus's moment of inertia factor is approximately 0.33, indicating the planet is differentiated with a denser core and lighter mantle, as expected. But small deviations from perfect symmetry in the gravity field could reveal remnants of the impact structure. The Magellan spacecraft measured these deviations to high precision in the early 1990s. The data showed Venus is remarkably symmetric. Any impact signatures have been erased by billions of years of internal convection and mantle flow. Detection methods for ancient giant impacts rely on indirect evidence. Astronomers cannot observe events that occurred 4 billion years ago. They must reconstruct the past from present measurements. For Venus, the primary evidence is the rotation itself. The backward spin stands as proof of catastrophic impact. Secondary evidence comes from Venus's lack of a moon. Earth's moon formed from a giant impact and has been orbiting for 4.5 billion years. Mars likely had small moons created by impacts that have since orbited stably for billions of years. Venus has no moon. Either the impact that reversed its rotation occurred at an angle and velocity that ejected debris beyond Venus's gravitational influence, or any orbiting debris later fell back to the planet. Computer simulations show both outcomes are possible depending on the precise impact parameters. Another detection method involves studying Venus's interior structure through seismology. On Earth, seismologists use earthquake waves to map the planet's interior, revealing the crust, mantle, outer core, and inner core with exquisite detail. Venus has no seismometers on its surface. The Soviet Venera landers in the 1970s and 80s operated for at most 2 hours before succumbing to the heat and pressure. They collected atmospheric data and surface images, but no seismic measurements. A future Venus lander equipped with a seismometer could detect Venus quakes and map the planet's interior. Asymmetries in the core mantle boundary or variations in seismic wave speeds could point to remnants of the giant impact. This data does not yet exist. We are left with rotation measurements and computer models. The transition from the impact moment to Venus's current state spans billions of years. Immediately after the collision, Venus would have been a molten sphere radiating intense heat into space. The surface temperature likely exceeded 2,000 degrees Celsius. Any atmosphere present before the impact would have been blown away. Over millions of years, the planet cooled. The magma ocean crystallized from the bottom up as heat radiated away. Volatiles trapped in the mantle outgassed, creating a new atmosphere rich in water vapor, carbon dioxide, and nitrogen. Venus might have had oceans during this period. Water vapor in the atmosphere would have created a greenhouse effect, warming the surface, but not necessarily to current hellish temperatures. The planet's slow backwards rotation, established by the impact, meant long days and nights, but the thick atmosphere would have distributed heat efficiently. Then something changed. Venus lost its water. The leading hypothesis invokes a runaway greenhouse effect. As Venus's atmosphere accumulated carbon dioxide from volcanic outgassing, surface temperatures rose. Warmer temperatures caused more water to evaporate from the oceans. Water vapor is itself a powerful greenhouse gas. More water in the atmosphere trapped more heat, raising temperatures further, causing more evaporation. The feedback loop spiraled out of control. Within perhaps a few 100 million years, Venus's oceans boiled away completely. Water vapor high in the atmosphere was broken apart by ultraviolet light from the sun into hydrogen and oxygen. The hydrogen, being light, escaped to space. The oxygen reacted with rocks on the surface, forming oxides. Venus became desiccated. This runaway greenhouse process connects directly to Venus's backwards rotation. Without a magnetic field generated by a dynamo effect, which requires faster rotation, Venus's atmosphere faced the solar wind directly. Charged particles from the sun stripped away lighter atmospheric gases preferentially. Hydrogen, the lightest element, was lost first and fastest. This accelerated the desiccation. A faster rotating Venus with a protective magnetic field might have retained its water. The collision that reversed the planet's spin thus set in motion a chain of events leading to the loss of Venus's oceans and any chance for life. The rotation and the lack of water are not separate facts. They are linked by physics and planetary evolution. Scientists measure Venus's water loss by studying the isotopic composition of hydrogen in the planet's atmosphere. Normal hydrogen has one proton. Deuterium, a heavy isotope, has one proton and one neutron. It is about twice as massive. When hydrogen escapes to space, the lighter normal hydrogen escapes more easily than deuterium. Over billions of years, this preferentially removes normal hydrogen, enriching the remaining atmosphere in deuterium. Venus's atmosphere today shows a deuterium to hydrogen ratio about 150 times higher than Earth's oceans. This indicates Venus has lost an enormous amount of hydrogen, consistent with the evaporation of oceans containing as much water as Earth's oceans or more. The measurements come from spectroscopy of Venus's atmosphere by ground-based telescopes and spacecraft, including the Venus Express orbiter, which operated from 2006 to 2014. The story of Venus's rotation thus expands into a story about planetary habitability, magnetic fields, atmospheric evolution, and the long-term consequences of giant impacts. The realization that Venus rotates backwards arrived late in human history. For 3 centuries, astronomers looked at Venus and saw what they expected to see. Giovanni Cassini, observing from Bologna in 1667, thought he detected surface markings through his telescope that appeared and disappeared with a period of about 23 hours. He published his estimate of Venus's rotation period as 23 hours and 21 minutes. The number seemed reasonable. Venus resembled Earth in size and mass. Surely it rotated at a similar rate. Cassini's reputation as an accomplished observer lent weight to the measurement. Subsequent astronomers accepted it without serious challenge for nearly 200 years. The problem was Venus's clouds. Unlike Mars, where surface features are clearly visible, or Jupiter, where cloud bands provide obvious rotation markers, Venus presents a featureless white disk to telescopes. The planet's thick atmosphere completely obscures the surface. What Cassini thought were surface markings were actually subtle variations in Venus's cloud tops, patterns that form and dissipate over days rather than rotating with the solid planet below. 19th century astronomers continued attempting to measure Venus's rotation, obtaining wildly different results. In 1890, Giovanni Schiaparelli, famous for his maps of Martian canals, proposed that Venus was tidally locked to the Sun, always presenting the same face to our star, just as the Moon always shows the same face to Earth. His estimate gave Venus a rotation period equal to its orbital period of 225 days. This seemed plausible. Mercury is tidally locked in a 3-to-2 resonance with the Sun. Venus, orbiting even closer, might be locked 1-to-1. Other astronomers disagreed. In the early 20th century, observers reported rotation periods ranging from 24 hours to 225 days. The measurements depended entirely on which cloud features observers chose to track and how they interpreted the apparent motions. Percival Lowell, observing from his private observatory in Flagstaff, Arizona, claimed to detect linear markings on Venus similar to the canals he believed he saw on Mars. He estimated a rotation period of around 30 days based on these features. Other observers saw no such markings. The controversy persisted because astronomy lacked the tools to penetrate Venus's clouds. Optical telescopes captured only reflected sunlight from the cloud tops. The solid planet beneath remained hidden. The breakthrough came from radar astronomy in the early 1960s. Radar uses radio waves instead of visible light. Radio waves at certain frequencies penetrate Venus's atmosphere and reflect off the solid surface. By measuring the Doppler shift in the reflected signal, scientists can determine the velocity of different parts of the planet's surface relative to Earth. If Venus rotates, one edge moves toward Earth while the opposite edge moves away. This creates a characteristic frequency spread in the reflected radar signal. The technique had been pioneered on the Moon in the late 1950s, where it confirmed the Moon's rotation period and resolved its orientation in space. In 1961, a team led by Roland Carpenter at the Jet Propulsion Laboratory transmitted radar pulses toward Venus using the Goldstone antenna in California's Mojave Desert. The reflected signals showed a frequency spread consistent with rotation, but the direction surprised everyone. The spread indicated retrograde rotation. Venus spun backwards. Carpenter's team was cautious. They repeated the observations and checked for instrumental errors. The results held. Independently, a group at MIT's Lincoln Laboratory, led by Richard Goldstein, obtained similar results using the Haystack Radar Facility in Massachusetts. By 1962, both teams published papers reporting that Venus rotates retrograde with a period of approximately 250 days, though the uncertainty was large, perhaps plus or minus 20 days. The astronomical community reacted with skepticism. Retrograde rotation violated expectations based on solar system formation theory. Planets should all rotate in the same direction. the radar measurements must be wrong. But as more observations accumulated through the 1960s, the retrograde rotation became undeniable. The Arecibo radio telescope in Puerto Rico, completed in 1963 and featuring a 305-meter dish, provided more powerful radar observations. By 1965, combined measurements from Arecibo, Goldstone, and Haystack narrowed Venus's rotation period to 243 days, with an uncertainty of about 5 days. The backwards rotation was real. The next challenge was understanding why. Theories proliferated. Some astronomers proposed that Venus's thick atmosphere, massing 90 times Earth's atmosphere, had gradually slowed and reversed the planet's rotation through tidal friction with the Sun. Others suggested peculiar initial conditions during planet formation. A third group, including planetary scientist William Hartmann, argued for a giant impact. Throughout the 1970s, these competing hypotheses were debated at conferences and in scientific papers. None had definitive evidence. The impact hypothesis seemed most consistent with the energy requirements, but without detailed computer simulations or additional data from Venus itself, the debate remained unsettled. Spacecraft missions transformed the understanding. NASA's Mariner 2 flew past Venus in 1962, confirming the planet's extreme surface temperature and dense atmosphere, but providing no rotation data. Mariner 5 followed in 1967, again a flyby. Mariner 10, en route to Mercury in 1974, passed Venus and returned ultraviolet images showing cloud patterns. By tracking these patterns over several days, scientists confirmed the atmosphere's superrotation, completing a circuit around the planet every 4 days, while the solid planet rotated far more slowly beneath. The Soviet Venera program achieved the first successful landings. Venera 7 survived on the surface for 23 minutes in 1970, transmitting temperature and pressure data. Venera 9 and 10 returned the first images from Venus's surface in 1975, showing rocky plains under orange skies. The real breakthrough for rotation measurements came with the Pioneer Venus orbiter, launched in 1978. The spacecraft entered orbit around Venus in December of that year and operated until 1992, far exceeding its planned mission lifetime. Pioneer Venus carried a radar altimeter that mapped large portions of the planet's surface, establishing reference features. By tracking these features over months and years, scientists refined the rotation period. In 1983, a paper published in the journal Icarus reported Venus's sidereal rotation period as 243.016 days, with an uncertainty of about 0.1 days. This represented a 100-fold improvement in precision over the early radar measurements. Technological advances enabled even better measurements. In 1990, NASA launched the Magellan spacecraft to Venus. Magellan carried a synthetic aperture radar that mapped 98% of Venus's surface at resolutions better than 100 meters. The mission operated from 1990 to 1994, repeatedly imaging the surface and measuring the gravity field. By tracking specific impact craters, mountains, and volcanic features across multiple orbits, scientists determined Venus's rotation period to unprecedented accuracy. The final value, published in 1996, gave 243.025 days, with an uncertainty of only 0.001 days. This precision revealed something unexpected. Venus's rotation rate varies. The variation is small, but measurable. Over the course of the Magellan mission and subsequent ground-based radar observations from 1990 through 2015, scientists detected changes in Venus's rotation period of up to 7 minutes. The planet speeds up and slows down slightly over years to decades. This phenomenon, published in Nature Geoscience in 2016 by a team led by Jean-Luc Margot at UCLA, results from the exchange of angular momentum between Venus's solid body and its massive atmosphere. Strong atmospheric winds pushing against mountains can torque the solid planet, altering its rotation speed. Earth experiences similar effects during El Niño events, when atmospheric circulation patterns change and the planet's rotation slows by a few milliseconds. Venus's variation is proportionally similar, but more dramatic in absolute terms because of the planet's slow rotation. The evolution of understanding Venus's backwards rotation spans 400 years, from Cassini's first observations to modern spacecraft missions. Early astronomers working with optical telescopes could only guess at the rotation period based on ambiguous cloud features. The development of radar astronomy in the mid-20th century provided the first reliable measurements and revealed the retrograde rotation. Spacecraft missions throughout the 1970s and 80s confirmed the radar data and provided context about Venus's atmosphere and surface. High-precision radar mapping in the 1990s established the rotation period to within seconds and discovered the subtle variations. Each technological advance refined the picture and raised new questions. Current theories about the origin of Venus's retrograde rotation rest on decades of computer modeling. The first serious simulations appeared in the 1980s using mainframe computers that performed millions of calculations. By the 2000s, advances in computing power enabled smoothed particle hydrodynamics simulations, with millions of particles running on supercomputer clusters. These simulations tested different impact scenarios, varying the impactor size from Mercury-sized objects about 5,000 kilometers in diameter to Mars-sized bodies around 7,000 kilometers across. They varied impact angles from nearly head-on collisions at 80 degrees, from horizontal to grazing impacts at 20 degrees. They varied impact velocities from 15 to 40 kilometers per second, covering the range of typical collision speeds in the early solar system. The results showed that only a narrow range of parameters produces Venus's current rotation state without destroying the planet. An impact by a Mars-sized object, roughly half Venus's mass, striking at 25 to 35 degrees from horizontal at velocities around 25 kilometers per second, consistently reversed the rotation while keeping the planet intact. Smaller impactors did not carry enough angular momentum. Larger ones or faster collisions destroyed both bodies. More oblique impacts tended to produce faster retrograde rotation than observed. The simulations also predicted that such an impact would have ejected several percent of the combined mass into space, with most of it either escaping Venus's gravity or eventually falling back. This explains the absence of a moon. The debris disk, if any formed, must have been short-lived. Comparative analysis with other planets strengthens the impact hypothesis. Uranus tilts on its side with an axial inclination of 98 degrees. The most likely explanation involves one or more giant impacts that knocked the planet over. Neptune's moon Triton orbits backwards, in retrograde motion around the planet. Triton almost certainly formed elsewhere in the solar system and was captured by Neptune, but the capture process required Triton to lose enormous orbital energy, likely through encounters with other moons that were subsequently ejected or destroyed. Earth's moon formed from the debris of a giant impact 4.5 billion years ago. Mercury's large iron core relative to its rocky mantle suggests a massive collision stripped away much of the original rocky material. Giant impacts shape the architecture of every terrestrial planet. Venus fits the pattern. What makes Venus's case special is the combination of retrograde rotation and extreme slowness. The impact had to impart backward spin without imparting too much backward spin. If Venus rotated backwards with a period of 50 days or 100 days, the impact parameters would need to be different. The actual 243-day period represents a very specific outcome. Some scientists have proposed that tidal forces from the Sun acting on Venus's massive atmosphere over billions of years have gradually slowed the initial post-impact rotation to its current rate. The math is contentious. Tidal slowing is a weak effect, and whether it can account for the specific rotation period remains debated. Recent discoveries add nuance to the story. In 2020, scientists analyzing archival radio occultation data from the Venus Express mission detected what might be gravitational signatures of past impacts. Recent discoveries add nuance to the story. In 2020, scientists add nuance to the story. In 2020, scientists analyzing archival radio occultation data from the Venus Express mission detected what might be gravitational signatures of past impacts in Venus's crust. Radio occultation measures how radio signals from a spacecraft bend as they pass through a planet's atmosphere and near its limb. Subtle variations in the bending reveal density variations in the upper atmosphere and, with careful analysis, in the solid planet beneath. The data showed anomalies in the gravity field at several locations that could represent buried impact basins or remnants of the giant collision that reversed Venus's rotation. The evidence remains tentative. The anomalies are small, near the detection threshold, and alternative explanations involving volcanic structures cannot be ruled out. But the possibility that we can still detect the ancient impact's gravitational fingerprint, even after 4 billion years, suggests the event was extraordinarily violent. Venus occupies a unique position in the solar system's architecture. It orbits at 0.72 astronomical units from the Sun, meaning it receives about 1.9 times the solar radiation Earth receives at 1 astronomical unit. This places Venus near the inner edge of the Sun's habitable zone, the region where liquid water could exist on a planet's surface. Different models define the habitable zone boundaries differently depending on assumptions about atmospheric composition and cloud coverage. Conservative models place the inner edge at about 0.95 astronomical units. Optimistic models extend it to 0.75 or even 0.7 astronomical units. Venus sits right on this boundary. With a different atmosphere or a different rotation, Venus might have remained habitable despite its proximity to the Sun. The relationship between orbital distance and rotation becomes apparent when comparing terrestrial planets. Mercury, at 0.39 astronomical units, is tidally locked to the Sun in a 3-to-2 resonance. It rotates 3 times for every 2 orbits, meaning Mercury's day lasts 58.65 Earth days, while its year takes 87.97 days. The tidal forces from the Sun, which fall off with the cube of distance, are strong enough at Mercury's orbit to have slowed its rotation over billions of years until it reached this stable resonance. Earth, at 1 astronomical unit, rotates every 24 hours. Tidal forces from the Sun and Moon gradually slow Earth's rotation by about 1.7 milliseconds per century, but the effect is weak. Mars, at 1.52 astronomical units, rotates every 24.6 hours, nearly identical to Earth. Tidal forces at Mars's distance are negligible. Venus, at 0.72 astronomical units, experiences stronger solar tides than Earth, but weaker than Mercury. If Venus rotated with a normal period of 24 hours and had a thin atmosphere, solar tides would eventually slow the rotation over many billions of years, perhaps locking it to the Sun like Mercury. But Venus does not have a thin atmosphere. Its 92-bar carbon dioxide atmosphere masses 80 times more than Earth's atmosphere. This massive atmosphere participates in the tidal interaction. The Sun's gravity raises tides not just in Venus's solid body, but in the atmosphere. These atmospheric tides create torques on the solid planet. Some scientists have proposed that atmospheric tides, combined with the peculiar retrograde rotation, have stabilized Venus's rotation period at exactly the value needed to create a resonance between Venus's day, its year, and Earth's orbit. The resonance, if real, is subtle. Venus's rotation period of 243.025 days combines with its orbital period of 224.7 days to produce a solar day, the interval between successive noons of 116.75 Earth days. 5 Venusian solar days equal 583.75 Earth days. This number is very close to 8 Earth years, which equal 2,922 days, and 13 Venus years, which equal 2,921.1 days. The near coincidence means that every time Venus and Earth reach their closest approach, called inferior conjunction, Venus presents nearly the same face to Earth. Over 8 Earth years, the alignment drifts by only a few degrees. Some astronomers argue this cannot be coincidence. The tidal influence of Earth on Venus's rotation, though weak, might have been sufficient over billions of years to nudge Venus's rotation period into this resonance. The mathematics supporting this resonance hypothesis involves calculating torques over geological time. Earth's gravitational pull on Venus is strongest at inferior conjunction when the planets are separated by only 0.28 astronomical units, or about 42 million kilometers. At this distance, Earth's tidal force on Venus is about 1/10,000th the solar tidal force, tiny but potentially significant over billions of orbits. If Venus's rotation period drifts slightly, due to core mantle friction or atmospheric exchange of angular momentum, the resonance with Earth would exert a restoring torque, pulling the rotation back toward the resonant value. Computer simulations by Carl Sagan and others in the 1970s explored this possibility. The results were inconclusive. The effect might be real, but uncertainties in Venus's internal structure and the strength of atmospheric coupling make definitive conclusions impossible. Measurement challenges complicate every attempt to understand Venus's rotation. The planet's surface temperature of 735 Kelvin, or 462 degrees Celsius, is hot enough to melt lead. Surface pressure exceeds 90 Earth atmospheres, equivalent to the pressure 1 kilometer beneath Earth's oceans. These conditions destroyed every lander sent to the surface within hours. The Soviet Venera landers, the most successful surface missions, survived for a maximum of 127 minutes. Venera 13, which landed in March 1982, holds the record. It transmitted temperature, pressure, and wind speed data, analyzed soil samples with an X-ray fluorescence spectrometer, and returned color images of the rocky surface. Then it failed. Modern electronics cannot operate at Venus surface conditions without extensive cooling systems, which are heavy and power-intensive. Orbital missions face different challenges. Venus's thick clouds extend from 48 to 70 kilometers altitude and consist primarily of sulfuric acid droplets. The clouds completely obscure the surface at visible wavelengths. Infrared light penetrates the clouds at certain specific wavelengths, allowing crude surface mapping. Radio waves penetrate readily, enabling radar mapping. But tracking surface features with sufficient precision to detect the 7-minute variations in rotation period requires repeated observations over years. Ground-based radar from Earth provides this capability, but Venus is visible from Earth only during certain parts of its orbit. For several months each year, Venus appears too close to the Sun in Earth's sky for radar observations. The observations must wait, introducing gaps in the data. Secondary effects of Venus's slow rotation ripple through the planet's entire system. The long day-night cycle on Venus lasts 116.75 Earth days from sunrise to sunrise. You might expect extreme temperature differences between day and night, with the day side baking under continuous sunlight and the night side freezing in perpetual darkness. This does not happen. Venus's thick atmosphere transports heat so efficiently that temperature variations between equator and poles, between day and night, and between different altitudes at the same pressure level amount to only a few degrees Kelvin. The surface temperature varies by less than 10 degrees across the entire planet. This remarkable thermal uniformity results from the atmosphere's superrotation and the massive heat capacity of 92 bars of carbon dioxide. The super-rotating atmosphere remains one of Venus's greatest mysteries. Wind speeds at cloud level, about 60 kilometers altitude, reach 350 kilometers per hour. These winds circle the planet in 4 Earth days, 60 times faster than the solid surface rotates beneath. The mechanism driving this super-rotation must extract energy from solar heating and convert it to atmospheric motion. Theoretical models propose that solar heating creates temperature differences between the day and night sides of the upper atmosphere. These temperature gradients drive waves, similar to ocean tides or atmospheric Rossby waves on Earth. The waves propagate around the planet and, through nonlinear interactions, transfer momentum to the mean flow, accelerating the winds. The process requires Venus's slow rotation. A faster spinning Venus would generate stronger Coriolis forces that would break up the circulation into multiple bands like Jupiter's atmosphere. Our position observing Venus from Earth shapes what we can measure and what remains hidden. Earth-based radar provides the longest baseline of observations, spanning from 1962 to the present, over 6 decades. This long timeline enables detection of the subtle rotation rate variations. But radar can only observe Venus when the planet is favorably positioned, and atmospheric conditions on Earth must be calm. Spacecraft missions provide close-up measurements but operate for limited durations. The Venus Express mission lasted 8 years. Magellan operated for 4 years. Combining data from different instruments on different platforms, each with distinct systematic errors, requires careful calibration and cross-checking. The perspective from Earth also biases our understanding toward observable phenomena. We know Venus's surface is young because it lacks impact craters older than about 500 million years. The entire surface appears to have been resurfaced by volcanic activity relatively recently. Whether this resurfacing happened suddenly in a global catastrophe or gradually over millions of years remains debated. We cannot answer this question definitively without seismic measurements or more detailed radar mapping than currently exists. The planet's interior structure, the size of its core, the presence or absence of a solid inner core, the viscosity of the mantle, all remain poorly constrained. Earth's interior structure is known in exquisite detail because thousands of seismometers have recorded millions of earthquakes. Venus has no seismometer network. We are left making educated guesses. Location in the habitable zone matters profoundly. Venus receives 90% more sunlight than Earth. If Venus had Earth's atmosphere and Earth's rotation, its surface temperature would be about 50 degrees Celsius, warm but potentially habitable in cooler regions near the poles or at higher elevations. The runaway greenhouse effect on Venus results from positive feedbacks involving water vapor and carbon dioxide. Once temperatures rose above the boiling point of water, all surface water evaporated. Water vapor trapped heat, raising temperatures further. Eventually, ultraviolet radiation from the sun dissociated water molecules high in the atmosphere into hydrogen and oxygen. The hydrogen escaped to space. This process transformed Venus from a potentially habitable world to an inferno. The backwards rotation influenced this transformation by preventing the formation of a protective magnetic field. Earth's magnetic field shields our atmosphere from the solar wind. Charged particles from the sun strike the magnetic field and are deflected around the planet. Some particles spiral down magnetic field lines near the poles, creating auroras, but most are kept away from the atmosphere. Venus lacks this protection. The solar wind strikes Venus's ionosphere directly, stripping away atmospheric gases. The loss rate is small, only a few hundred tons per day, but over billions of years the cumulative loss is substantial. Measurements by the Venus Express spacecraft from 2006 to 2014 tracked ion escape rates and confirmed that Venus loses hydrogen preferentially, consistent with the high deuterium to hydrogen ratio. The implications for exoplanet habitability are direct. Astronomers have discovered thousands of planets orbiting other stars. Many of these exoplanets orbit within their star's habitable zone. Determining whether these worlds actually host life requires understanding what makes a planet habitable beyond simple distance from the star. Rotation rate matters. Tidal locking, common for planets orbiting close to dim red dwarf stars, creates permanent day and night sides that may preclude habitability. Slow retrograde rotation like Venus might prevent magnetic field generation, exposing the atmosphere to stellar wind erosion. Atmospheric composition matters. A runaway greenhouse can transform an Earth-like world into a Venus-like hell. 5. Atmospheric composition matters. A runaway greenhouse can transform an Earth-like world into a Venus-like hell. Fast rotation enables magnetic field generation, which protects atmospheres from stellar wind erosion. Venus demonstrates that habitable zone location alone does not guarantee habitability. The planet's history serves as a cautionary tale for exoplanet studies and raises uncomfortable questions about Earth's long-term future as the sun gradually brightens over billions of years. The scientific community remains divided on the fundamental question of what caused Venus's retrograde rotation. Two competing frameworks offer different explanations, predict different observable signatures, and carry different implications for planetary formation theory. The disagreement is not merely academic. The answer determines whether Venus's fate was sealed by a single catastrophic event 4 billion years ago, or by slow, inexorable tidal forces acting over the planet's entire lifetime. The distinction matters for understanding how often retrograde rotation occurs in planetary systems, and whether Venus-like worlds orbiting other stars might have avoided the same fate. The giant impact hypothesis, championed by planetary scientists including Robin Carnap at the Southwest Research Institute and Willy Benz at the University of Bern, proposes that Venus originally rotated prograde like other planets. During the late heavy bombardment approximately 4 billion years ago, a Mars-sized impactor struck Venus at an oblique angle. The collision transferred enough angular momentum to completely reverse the planet's spin. Computer simulations using smoothed particle hydrodynamics support this scenario. Models published in Icarus in 2009 showed that an impactor with a mass between 0.3 and 0.5 times Venus's mass, striking at 25 to 35 degrees, from vertical at velocities near 25 kilometers per second, consistently produces retrograde rotation with periods ranging from 150 to 300 days. The simulations predict that Venus should have lost several percent of its mass to space during the collision, explaining the absence of a large moon. The impact hypothesis makes specific predictions that can be tested. First, Venus's interior should show asymmetries or compositional variations resulting from incomplete mixing of the impactor's material with the original planet. The impactor's iron core should have merged with Venus's core, but the mixing might not be perfect. Variations in the ratio of heavy-to-light elements with depth could reveal the impact signature. Second, the planet's moment of inertia, the distribution of mass with radius, should reflect the post-impact structure. Third, if the impact occurred 4 billion years ago, subsequent tidal evolution over billions of years should have modified Venus's rotation period from its initial post-impact value to the current 243.025 days. The hypothesis requires calculating this tidal evolution and showing it matches observations. The atmospheric tidal hypothesis, developed by Alexandra Correa at the University of Aveiro and Jacques Lascar at the Paris Observatory, proposes something entirely different. Venus might have formed with retrograde rotation, or its rotation might have been reversed by atmospheric tides alone, without any giant impact. The key insight is that Venus's massive atmosphere interacts strongly with solar tides. The Sun's gravity raises thermal tides in the atmosphere as solar heating creates pressure bulges on the day side. These pressure variations exert torques on the solid planet. Over hundreds of millions to billions of years, these torques can slow an initial prograde rotation, bring it to a halt, and then accelerate the planet in the retrograde direction. Papers published in Nature in 2003 and in Astronomy and Astrophysics in 2008 showed that thermal atmospheric tides can drive Venus's rotation into a stable retrograde state without requiring any impact. The atmospheric tidal model makes its own predictions. The current rotation period should represent an equilibrium state where atmospheric torques balance other effects like core mantle friction. Small perturbations to the rotation rate should be damped by atmospheric coupling on timescales of decades to centuries. This prediction matches observations. Venus's rotation period varies by up to 7 minutes over decades, precisely as expected if atmospheric angular momentum exchanges with the solid planet. The model also predicts the near resonance between Venus's solar day and Earth-Venus synodic period. Earth's tidal influence, though much weaker than solar tides, may have helped lock Venus into its current rotation state over billions of years. The disagreement between these frameworks amounts to fundamentally different views of Venus's history. Impact advocates point to the statistical improbability of retrograde rotation. Of 8 planets in the solar system, only Venus spins backwards. Random formation processes should produce equal numbers of prograde and retrograde rotators. The fact that 7 planets rotate prograde while only 1 rotates retrograde suggests retrograde rotation requires special circumstances like a giant impact. The probability that Venus randomly formed with retrograde rotation purely from local disk conditions is less than 10% based on planet formation simulations. Atmospheric tides could not reverse a fast prograde rotation before the massive atmosphere accumulated, and the atmosphere required millions of years to outgaze after the planet formed. Tidal advocates counter that Venus's orbit and atmospheric properties make it uniquely susceptible to tidal spin reversal. They calculate that an initial rotation period slower than about 10 days could be reversed by atmospheric tides within 1 billion years. If Venus formed with an initial rotation period of 7 to 8 days, plausible for a planet assembled from lower angular momentum material in the inner disk, atmospheric tides alone suffice. The absence of a moon supports this view. A giant impact energetic enough to reverse rotation should have created a debris disk that formed a moon, as happened with Earth. Venus has no moon, suggesting no giant impact occurred. The tidal hypothesis requires no special events, only the physics of atmospheric heating and gravitational torques operating over geological time. The numerical disagreement focuses on the timescale for rotation reversal. Impact models calculate that a Mars-sized collision transfers sufficient angular momentum to reverse Venus's rotation essentially instantaneously on geological timescales. The impact itself lasts hours. The planet re-equilibrates over millions of years as the mantle solidifies and volatiles outgas. Subsequent tidal evolution over 4 billion years could then modify the rotation period by tens of %. Correa and Laska's tidal models calculate that reversing a 10-day prograde rotation to a 243-day retrograde rotation via atmospheric tides requires approximately 1.5 billion years under Venus's atmospheric conditions. The difference in timescales, billions of years versus hours plus tidal modification, has implications for when Venus lost its habitability. If the giant impact hypothesis is correct, Venus's rotation was reversed early, perhaps 4 billion years ago. The planet then had billions of years to evolve atmospherically and lose its water. The slow rotation contributed to the lack of a magnetic field throughout this period, but the impact itself was a one-time event. If the tidal hypothesis is correct, Venus might have retained fast prograde rotation and a protective magnetic field for the first billion years of its history. During this period, the planet could have had oceans and remained potentially habitable. Only as atmospheric tides gradually slowed and reversed, the rotation did Venus lose its magnetic field and begin the irreversible transformation to its current state. The habitability window differs by billions of years between the two scenarios. The stakes extend beyond Venus. Exoplanet surveys have discovered super-Earths and sub-Neptunes orbiting in the habitable zones of red dwarf stars. These planets often orbit so close to their dim stars that tidal forces are strong. Many are probably tidally locked, rotating once per orbit, with permanent day and night hemispheres. But some might be in states similar to Venus, with thick atmospheres and slow or retrograde rotation maintained by atmospheric tides. Without knowing which mechanism produced Venus's retrograde rotation, we cannot predict how common such states are or whether they preclude habitability. If giant impacts are required, retrograde rotation should be rare. If atmospheric tides suffice, any Venus-like world with a massive atmosphere might naturally evolve toward retrograde rotation. Both hypotheses should produce observable differences in Venus's interior structure, yet neither has been conclusively confirmed or ruled out. This is the heart of the scientific tension. The giant impact hypothesis predicts compositional heterogeneities or asymmetries in the core or deep mantle from incomplete mixing of the impactor. The tidal hypothesis predicts a more uniform interior structure similar to what would result from undisturbed accretion. Measurements of Venus's gravitational field by the Magellan mission showed the planet is remarkably symmetric. The gravity field's low-degree harmonics, which reflect the planet's overall shape and internal density distribution, are smaller than expected for a world with recent resurfacing or impact-induced asymmetries. This might support the tidal hypothesis. But 4 billion years of mantle convection could have erased impact signatures, making the observation ambiguous. The rotation period's stability or lack thereof provides another test. If atmospheric tides actively maintain Venus's rotation in an equilibrium state, the rotation period should vary on human observable timescales as atmospheric conditions change. Observations confirm this. Jean-Luc Margot's team at UCLA measured rotation period variations of up to 7 minutes over the 16-year interval from 1996 to 2012 using radar observations from Earth. The variations correlate with changes in Venus's atmospheric superrotation detected by spacecraft. When cloud-level winds speed up, the solid planet slows slightly. When winds slow, the planet speeds up. The total angular momentum of the solid planet plus atmosphere remains roughly constant, confirming that atmospheric coupling is real and significant. This behavior is exactly what the tidal hypothesis predicts. Impact advocates argue it does not rule out an impact. Atmospheric coupling operates regardless of how Venus initially acquired its retrograde rotation. Debate continues over the resonance with Earth. Venus's solar day of 116.75 Earth days means that every 8 Earth years, Venus completes almost exactly 5 solar days and returns to nearly the same orientation relative to Earth. Some scientists calculate that this resonance is statistically significant at the 3 sigma level, meaning the probability it occurred by chance is less than 1 in 300. If real, the resonance suggests Earth's tidal influence on Venus has been important over geological time, supporting the tidal hypothesis. Skeptics point out that with 8 planets, dozens of moons, and hundreds of measurable orbital and rotational periods in the solar system, finding a few near commensurabilities by chance is expected. The 3 sigma significance might be illusory, a result of selecting the resonance after observing it rather than predicting it beforehand. The implications for planetary formation models are profound. Standard models assume planets form with rotation periods determined by the angular momentum of the material that accreted to build them. For rocky planets in the inner solar system, formation models typically predict initial rotation periods between 8 and 24 hours. Venus's current 243-day period is an outlier by 2 orders of magnitude. If giant impacts routinely reverse rotations, then measured rotation periods tell us little about formation conditions. They reflect post-formation collision history instead. If atmospheric tides can reverse rotations given the right planetary properties, then any planet with a sufficiently massive atmosphere and slow initial rotation might naturally evolve toward retrograde states. Models must incorporate atmospheric tidal evolution from the beginning, not treat it as a minor perturbation. The disagreement also affects how we interpret Mercury. That planet rotates 3 times for every 2 orbi for every 2 orbits in a stable spin-orbit resonance. For decades, astronomers assumed Mercury was tidally locked 1-to-1 with the Sun, always showing the same face like the Moon does to Earth. Radar observations in 1965 by Gordon Pettengill and Rolf Dice proved this wrong. Mercury rotates faster than it orbits, completing 3 rotations in 2 orbits. This 3-to-2 resonance is stable because Mercury's orbit is elliptical. When Mercury passes perihelion, its closest approach to the Sun, tidal forces are strongest. The resonance ensures Mercury presents the same face to the Sun at alternate perihelion passages. If atmospheric tides can reverse planetary rotations, then Mercury's resonance might not be purely a consequence of solid body tides. Mercury has essentially no atmosphere, only a tenuous exosphere, so atmospheric tides do not apply. But the question becomes whether we understand tidal evolution as well as we think. Venus's backwards rotation defies intuition in ways that go beyond simple direction. The planet does not merely spin the wrong way. It spins so slowly that astronomical measurements required to pin down the exact period took decades, despite modern technology. Think about observing Venus from its surface. The Sun rises in the west, climbs slowly across the sky over 58 Earth days, sets in the east, and remains below the horizon for another 58 Earth days. During the Sun's transit from western horizon to eastern horizon, Venus moves more than halfway around its orbit. An observer on Venus would see the Sun moving backwards against the background stars. The stars would rise in the east and set in the west, as they do on Earth because Venus's rotation is retrograde. But the Sun moves the opposite direction because the orbital motion partially counteracts the rotation. Here is an analogy that captures the strangeness. Imagine standing on a slow-moving carousel that rotates counterclockwise, completing one rotation every 4 minutes. You are walking clockwise around the carousel's edge at a pace that takes 3.5 minutes to complete a circuit. From the perspective of someone standing still outside the carousel, you are moving in a complex path. But from your perspective, standing on the carousel, you are walking forward while the carousel pulls you backwards. The net result is that you advance slowly in your walking direction. But the landmarks around the carousel appear to move backwards relative to you. Venus's sun behaves like those landmarks. Venus rotates backwards slowly. Venus orbits forwards faster. The sun appears to move backwards in Venus's sky, but more slowly than the rotation alone would cause. The observational evidence for this counterintuitive situation comes from tracking cloud features and surface landmarks over time. Venus's clouds race around the planet in 4 days, super-rotating independently of the surface. An observer floating at cloud level would experience one day-night cycle every 2 Earth days, as the fast-moving atmosphere carries them around the planet. But the surface beneath rotates slowly backwards, completing one rotation every 243 days. This creates a shear between the surface and the atmosphere, with wind speeds varying dramatically with altitude. Near the surface, winds blow at only a few meters per second, barely noticeable. At cloud level 60 kilometers up, winds reach 100 meters per second or 360 kilometers per hour. The wind speed increases with altitude following a complex vertical profile that depends on temperature, pressure, and solar heating. Simulations of planetary rotation struggle to reproduce Venus's exact state. When researchers model the formation of the solar system using thousands of planetary embryos colliding and merging over tens of millions of years, the final planets almost always rotate prograde with periods between 10 and 40 hours. Retrograde rotations occur in less than 5% of simulations, and rotation periods longer than 100 days are even rarer. To get Venus-like rotation, simulations must either include a specific late giant impact or invoke atmospheric tidal evolution after the planet forms. Neither occurs naturally in most runs. The simulations must be fine-tuned to produce Venus's observed state, suggesting either the models are missing important physics or Venus's rotation represents an unlikely outcome. Reality has produced exactly one retrograde rotator among 8 planets. The statistical improbability of this result under random formation conditions is high. If each planet had an independent 50% chance of rotating prograde or retrograde, the probability that 7 rotate prograde and only 1 retrograde equals 8 times 0.5 to the 8th power, or about 3%. We observed this 3% outcome, but formation physics is not random. Conservation of angular momentum strongly favors prograde rotation for planets forming from a rotating disk. The probability of retrograde rotation from formation alone is likely far less than 50%, perhaps less than 10%. This makes Venus's retrograde rotation a 5 sigma or greater outlier, something that should happen by chance in fewer than 1 in a million solar systems. Either Venus experienced unusual circumstances or our understanding of planetary formation is incomplete. Alternative frameworks have been proposed to explain Venus without invoking rare events. One hypothesis suggests Venus formed in a different orbital location and migrated inward to its current position at 0.72 astronomical units. During migration, resonances with other planets or gravitational interactions with the remnant gas disk could have altered Venus's rotation. Computer simulations of planetary migration in the early solar system show that planets can exchange angular momentum through resonant interactions. If Venus migrated through a resonance with Earth or Mercury, the encounter might have slowed or reversed its rotation. However, dynamical models of the inner solar system's evolution show little evidence for large-scale migration. The terrestrial planets appear to have formed close to their current orbits and remained roughly in place for 4 billion years. Migration cannot easily explain Venus. Another alternative proposes that Venus experienced multiple giant impacts rather than one. A series of smaller collisions over hundreds of millions of years during the late heavy bombardment could have gradually slowed Venus's prograde rotation, brought it to a halt, and then accelerated it in the retrograde direction. Each impact would transfer angular momentum in an amount depending on the impactor's mass, velocity, and angle. The cumulative effect might produce retrograde rotation without requiring a single catastrophic Mars-sized collision. This hypothesis has the advantage of not requiring a specific low-probability event. Giant impacts were common during the late heavy bombardment. Multiple impacts are more likely than one perfect impact. The disadvantage is that most simulations of multiple collisions produce chaotic spin states, with the planet's rotation axis wobbling and the rotation period varying wildly. Stabilizing the rotation at Venus's current state requires the impacts to occur in a specific sequence, which reintroduces fine-tuning. Modified theories of planetary formation attempt to explain Venus's rotation from first principles. Some researchers propose that Venus and Earth formed as a binary planet system early in solar system history. The two planets orbited a common center of mass, tidally interacting. Earth accreted the moon-forming impactor, which disrupted the binary system and ejected Venus into a highly elliptical orbit. Subsequent dynamical evolution circularized Venus's orbit while leaving it with retrograde rotation. This scenario requires extreme initial conditions and has difficulty matching the current orbits of Earth and Venus, which are nearly circular and coplanar. The hypothesis remains speculative without supporting evidence. Other modified theories focus on Venus's atmosphere. Perhaps Venus formed with a much thicker primordial atmosphere, captured directly from the solar nebula before the gas disk dissipated. This massive hydrogen-helium envelope could have interacted with the forming planet, extracting angular momentum and slowing or reversing the rotation. Over hundreds of millions of years, ultraviolet radiation from the young sun would have stripped away the hydrogen and helium, leaving behind the carbon dioxide atmosphere we observe today. Venus Express measurements showed that Venus loses atmospheric gases to space at significant rates even now. Extrapolating backwards, Venus could have had a much more massive atmosphere early in its history. But whether such an atmosphere could reverse a planet's rotation remains uncertain. The physics of gas-planet interaction in a protoplanetary disk is complex and poorly understood. The backwards rotation creates an unexpected asymmetry in how Venus responds to solar tides. On Earth, the Moon's gravity raises tides in the oceans that create a bulge slightly ahead of the Moon's position due to friction and the time lag in how water responds. This bulge exerts a gravitational pull on the Moon, gradually transferring angular momentum from Earth's rotation to the Moon's orbit. Earth's rotation slows. The Moon spirals outward. The system evolves toward a state where Earth and Moon would be tidally locked, both always showing the same face to each other, though this end state lies billions of years in the future. Venus experiences similar tidal effects from the Sun, but the retrograde rotation reverses the interaction. The tidal bulge lags behind the Sun's position when viewed from above Venus's north pole. This geometry means tides should slow Venus's retrograde rotation over time, making the planet spin less backwards, eventually bringing it to a halt. Given enough time, tides might even reverse the retrograde rotation back to prograde. Calculations of this tidal evolution depend sensitively on assumptions about Venus's interior properties. The strength of tidal dissipation, measured by the tidal quality factor Q, determines how much energy is lost to friction as the planet flexes under tidal forces. Earth's Q factor is approximately 50 for solid body tides. The Moon's Q factor is close to 100. Venus's Q factor is unknown, but estimated to lie between 30 and 200 based on theoretical models. A low Q factor means strong dissipation and rapid tidal evolution. A high Q factor means weak dissipation and slow evolution. Over 4 billion years, tides could have changed Venus's rotation period by anywhere from a few days to several hundred days, depending on the Q factor. This uncertainty prevents definitive conclusions about whether Venus's current rotation is consistent with an initial post-impact state or represents a later equilibrium maintained by atmospheric tides. The rotation axis adds another layer of complexity. Venus's axial tilt, the angle between its rotation axis and the perpendicular to its orbital plane, measures only 2.6 degrees. This is the smallest axial tilt of any planet. Earth tilts 23.4 degrees, giving us seasons. Mars tilts 25 degrees. Uranus tilts 98 degrees, rolling on its side. Venus's nearly upright rotation axis suggests either the planet formed with no tilt and maintained it through billions of years, or the tilt was damped by some mechanism. A giant impact should have knocked Venus's axis into a tilted orientation. Over time, tidal forces from the Sun can damp axial tilts, pulling the rotation axis toward perpendicular to the orbit. For Venus's small mass and distance from the Sun, this damping timescale is estimated at several billion years. The current 2.6 degree tilt could represent the end state of tidal damping that began with a larger tilt after a giant impact. Alternatively, the small tilt might indicate no giant impact occurred, supporting the atmospheric tidal hypothesis. Observational tests to distinguish between competing hypotheses require measurements we cannot yet make. Seismic data would reveal Venus's internal structure and show whether compositional asymmetries from a giant impact persist. A long-duration lander capable of surviving months or years on Venus's surface could deploy seismometers and measure Venus quakes. No such mission has been attempted. NASA's proposed Veritas mission, scheduled for launch in the late 2030s, would orbit Venus and map the surface with synthetic aperture radar at 10 times better resolution than Magellan achieved. Veritas might detect subtle topographic or gravitational signatures of ancient impacts. But detecting signals from an event 4 billion years old, after billions of years of volcanic resurfacing and mantle convection, may prove impossible. The philosophical implications are disquieting. We observe Venus today and try to reconstruct its history from snapshots. The planet offers only indirect clues. Its rotation is backwards and slow. Its surface is young, its atmosphere is massive, its interior is symmetric. From these observations, we construct narratives about giant impacts or tidal evolution, testing them with simulations. But the simulations require assumptions about initial conditions, material properties, and timescales that we cannot verify. The true history remains hidden, orchestrating measurement techniques and historical mission details. The true history remains hidden beneath layers of clouds and centuries of cooling rock. What we can access are the measurements themselves, the techniques that revealed Venus's backwards rotation, and continue to refine our understanding with each observation. The methods span from ground-based radar-bouncing radio waves off a planet 30 million kilometers away to spacecraft orbiting through sulfuric acid clouds mapping every mountain and crater. Each technique extracts different information. Each has its own precision limits and systematic errors. Together, they have constructed the portrait of Venus's rotation we possess today, a picture that grows sharper, but never quite complete. Radar astronomy provided the breakthrough that revealed Venus's retrograde rotation. The technique works by transmitting a powerful radio pulse toward Venus and measuring the echo that returns. The transmitted signal has a precise frequency, typically in the S-band around 2.4 GHz or X-band around 8.5 GHz. As the radio waves reflect off Venus's surface, the Doppler effect shifts the frequency. Points on Venus's surface moving toward Earth reflect signals shifted to higher frequencies. Points moving away shift to lower frequencies. If Venus rotates, one edge of the visible disk moves toward Earth, while the opposite edge moves away, creating a characteristic spread in the reflected signal's frequency spectrum. Measuring this spread reveals the rotation rate. Measuring which edge produces the higher frequency return reveals the direction of rotation. The Goldstone Solar System radar, located in California's Mojave Desert, began systematic observations of Venus in 1961. The facility uses a 70-meter diameter antenna that can transmit up to 500 kilowatts of radio power at X-band frequencies. When the antenna transmits toward Venus, the radio waves spread out as they travel through space. By the time they reach Venus, the power density has dropped to about 1/1,000,000th of a watt per square meter. Venus reflects roughly 10% of this energy back toward Earth. The return signal reaching Goldstone has a power density of only 10 to the -23 watts per square meter. The antenna collects this incredibly faint signal and amplifies it using cryogenically cooled receivers with noise temperatures below 20 Kelvin. Even with these advanced systems, detecting Venus's echo requires integration times of several minutes to build up sufficient signal-to-noise ratio. The Arecibo Observatory in Puerto Rico, which operated from 1963 until its collapse in 2020, provided even more powerful radar observations. Its 305-meter dish was nearly 3 times the diameter of Goldstone, collecting 9 times more signal power. Arecibo transmitted up to 1 megawatt at S-band frequencies. The larger aperture also provided better angular resolution, allowing scientists to distinguish returns from different regions of Venus's surface. By measuring the frequency spread and the distribution of returned power across the spectrum, Arecibo observations in the 1970s determined Venus's rotation period to within a few days. Later observations through the 1980s and 90s, as receiver technology improved, narrowed the uncertainty to less than 1 day. Information extraction from radar data requires careful analysis. The returned signal contains contributions from the entire visible hemisphere of Venus, roughly half the planet. The center of the disk reflects signals back with minimal Doppler shift, because those points move perpendicular to the line of sight. The edges produce maximum Doppler shift. The exact shape of the frequency spectrum depends on the rotation rate, the size of the planet, and the viewing geometry determined by Venus's orbital position and orientation. Scientists model these geometric factors and compare the observed spectrum to predictions for different rotation periods and directions. The retrograde rotation signature is unmistakable. The edge of Venus moving away from Earth based on its orbital motion actually produces the higher frequency return, indicating it moves toward Earth due to rotation. Only backwards rotation can produce this reversal. Characteristic scales emerge from the radar measurements. Venus's radius is 6,051.8 kilometers, only about 600 kilometers smaller than Earth's. At this radius, a point on Venus's equator travels 2.6 meters per second due to the planet's rotation. This velocity is tiny compared to Earth's equatorial rotation speed of 463 meters per second, but it is measurable with modern radar. The Doppler shift from 2.6 meters per second motion amounts to only 46 Hertz at X-band frequencies, requiring frequency resolution better than 10 Hertz to detect. Radar systems achieve this through long integration times and advanced signal processing. The measurements become more precise as Venus approaches Earth during inferior conjunction, when the planet is closest and the return signal strength peaks. Independent confirmation came from spacecraft carrying radar systems into orbit around Venus. The Pioneer Venus orbiter, launched in 1978, carried a radar altimeter that mapped the planet's topography over 4 years of operation. The altimeter sent radio pulses downward and measured the time delay for echoes to return, determining the height of surface features. By tracking specific mountains and impact craters over hundreds of orbits, scientists could measure how these landmarks shifted position as Venus rotated. The spacecraft's orbital period was 24 hours, so each orbit showed Venus rotated by about 1.48 degrees, or 1/243rd of a full rotation. Over the mission's 4-year lifetime, Pioneer Venus observed Venus complete 6 full rotations. The accumulated position measurements yielded a rotation period of 243.09 days, with an uncertainty of about 0.3 days. The Magellan mission, which orbited Venus from 1990 to 1994, revolutionized our knowledge of Venus's surface and rotation. Magellan carried a synthetic aperture radar that achieved resolution as fine as 100 meters, revealing details smaller than a football field. The spacecraft mapped 98% of Venus's surface, repeatedly imaging the same regions on different orbits. Synthetic aperture radar works by combining returns from many transmitted pulses as the spacecraft moves along its orbit. The motion creates an effectively larger antenna aperture, improving resolution beyond what the physical antenna size allows. Magellan's 12.6 centimeter wavelength radar penetrated Venus's clouds effortlessly and mapped the solid surface beneath. By tracking the position of distinctive features like impact craters, volcanic domes, and mountain peaks across multiple mapping cycles, scientists measured Venus's rotation with unprecedented precision. The technique is straightforward in principle. Identify a landmark in an image from the first mapping cycle. Find the same landmark in an image from the second cycle. Measure how far the landmark moved. Divide the distance by the time elapsed between images. This gives the rotation rate. In practice, the analysis is complex. The viewing geometry differs between orbits. The spacecraft's position and velocity must be known precisely. Distortions from the radar imaging process must be corrected. Atmospheric refraction shifts the apparent position of surface features slightly. Accounting for all these effects required years of careful work by radar scientists at the Jet Propulsion Laboratory and NASA's Goddard Space Flight Center. The final Magellan rotation period, published in 1996, gave 243.0250 days, with an uncertainty of only 0.0015 days. This represented better than 1 part in 100,000 precision. The measurement also revealed something unexpected. Comparing Magellan's determination with earlier measurements from Pioneer Venus and ground-based radar showed small discrepancies. The rotation period appeared to vary by several minutes over decades. At first, scientists suspected systematic errors in one or more datasets. Different techniques measure rotation differently. Ground-based radar samples the visible hemisphere during each observation. Spacecraft track specific landmarks. Perhaps the techniques were not measuring exactly the same thing. But as more data accumulated, the variation persisted. Recent advances confirmed the rotation period variations are real. A team led by Jean-Luc Margot at UCLA published results in Nature Geoscience in 2016, using ground-based radar observations from Goldstone, spanning 1996 to 2012. They measured Venus's rotation period at multiple epochs, separated by years. The data showed variations up to 7 minutes in length, meaning Venus rotates faster or slower by about 0.3% over timescales of years to decades. The variations correlate with changes in Venus's atmospheric superrotation measured by spacecraft. When winds at cloud level speed up, the solid planet slows slightly. When atmospheric winds slow down, the planet speeds up. The correlation is not perfect, suggesting other factors also play a role, but the overall pattern is clear. Venus's rotation period is not constant. This discovery has implications for understanding the planet's interior. Earth's rotation varies by milliseconds over years due to exchanges of angular momentum with the atmosphere, oceans, and liquid outer core. Venus's larger rotation variations relative to the mean rotation period, 0.3% compared to Earth's variations of less than 0.01%, indicate stronger coupling between Venus's atmosphere and its solid body. The coupling could occur through winds pushing against mountains, creating torques. It could involve electromagnetic interactions if Venus's core generates weak, transient magnetic fields. Or it could reflect tidal effects from the Sun and Earth that vary as Venus's orbital position changes. Distinguishing between these mechanisms requires more detailed observations of atmospheric winds, surface topography, and interior structure than currently available. Precision improvements continue as technology advances. Modern radar systems at Goldstone and the newly constructed 500-meter FAST telescope in China achieve signal-to-noise ratios 10 times better than 1980s-era systems. Better receivers, more powerful transmitters, and improved signal processing extract more information from each observation. Future ground-based radar facilities could measure Venus's rotation period to better than 1 second accuracy, detecting even smaller variations over shorter timescales. Such measurements would constrain models of core-mantle interaction and atmospheric coupling, revealing how energy and angular momentum flow through Venus's interior. Future orbital missions will carry advanced radar systems building on Magellan's success. NASA's Veritas mission, currently scheduled for launch in the late 2030s, will map Venus with synthetic aperture radar achieving 10-meter resolution, 100 times better than Magellan. At this resolution, individual boulders and small volcanic features become visible. Tracking these features across multiple mapping passes will measure local variations in rotation rate, testing whether different regions of Venus's surface rotate at slightly different speeds, as they would if the crust slides over the mantle. The mission will also carry a radio science package that tracks the spacecraft's motion with millimeter precision, measuring Venus's gravity field in far greater detail than Pioneer Venus or Magellan achieved. Gravity variations reveal density variations in the crust and upper mantle, potentially showing buried impact basins or other structures. The European Space Agency's Envision mission, planned for launch in the early 2030s, will complement Veritas with different instruments. Envision carries a subsurface radar that transmits signals at frequencies low enough to penetrate kilometers into Venus's crust, revealing layered structures and buried features invisible to surface mapping radar. The mission also includes spectrometers that map the composition of surface rocks and monitor volcanic activity. Together, Veritas and Envision will provide the most comprehensive view of Venus since Magellan, potentially answering long-standing questions about the planet's geological history and internal structure. Even more ambitious proposals envision balloon missions that would float in Venus's upper atmosphere for months, measuring atmospheric dynamics, chemistry, and energy transport. At altitudes around 60 kilometers, where cloud-level temperatures hover near 0 degrees Celsius and pressures match Earth's surface, balloons can operate with conventional electronics. A swarm of balloons equipped with weather sensors and cameras could map how super-rotating winds vary with latitude, altitude, and time, testing models of what drives the atmospheric circulation. If the balloons carried radar transponders, ground-based radar could track their positions precisely, measuring wind speeds at cloud level to better than 1 meter per second. These atmospheric measurements connect directly to understanding rotation because the winds exchange angular momentum with the solid planet, influencing the rotation period on observable timescales. The measurement challenge fundamentally comes down to observing a slow process with limited tools. Venus rotates once every 243 days. To measure the rotation precisely requires observing for multiple rotations, which takes years. The measurement challenge fundamentally comes down to observing a slow process with limited tools. Venus rotates once every 243 days. To measure the rotation precisely requires observing for multiple rotations, which takes years. Small errors in individual measurements propagate through the analysis. Yet despite these difficulties, astronomers have tracked specific features on Venus's surface with remarkable precision, building a library of landmarks that serve as reference points for rotation studies. These features tell stories of their own, revealing how Venus's surface evolves even as the planet spins beneath its clouds. Crater Meade stands as one of Venus's most distinctive landmarks. Located at 12.5 degrees north latitude and 57.2 degrees east longitude, this impact crater measures 270 kilometers across, making it the largest impact structure on Venus. Magellan's radar images showed Meade's floor is remarkably flat and smooth, suggesting lava flooded the crater after the impact. The crater's rim rises about 1 kilometer above the surrounding plains. Multiple concentric rings surround the central depression, characteristic of large, complex craters formed by asteroids or comets, striking at velocities of 20 kilometers per second or more. Scientists have used Meade as a reference landmark since the Magellan mission. By measuring Meade's longitude in successive radar observations from Earth, they track how Venus rotates beneath the coordinate system defined by the International Astronomical Union. Observations of Meade between 1990 and 2012 showed the crater moved westward at a rate corresponding to Venus's retrograde rotation. But the motion was not perfectly uniform. In some observation windows, Meade appeared slightly ahead of its predicted position. In others, it lagged behind. The variations amounted to only a few kilometers, but at Venus's slow rotation rate, a few kilometers of displacement corresponds to several minutes of rotation period change. These small shifts in Meade's position provided some of the clearest evidence that Venus's rotation rate varies with time. The crater itself has not moved relative to Venus's surface. The entire planet rotates faster or slower, carrying Meade with it. Maxwell Montes represents another crucial reference feature. This mountain range, located at 65 degrees north latitude near Venus's North Pole, rises to an elevation of 11 kilometers above the mean radius, making it the highest point on Venus. Maxwell is taller than Mount Everest if measured from base to peak. The range stretches for 800 kilometers in an east-west direction and displays evidence of thrust, faulting and folding, suggesting tectonic compression formed the mountains. Unlike Meade Crater, which has a well-defined center point easy to identify in radar images, Maxwell Montes extends over a large area. Scientists track specific peaks within the range, using their latitude and longitude as reference markers. Observations spanning 3 decades show Maxwell's position shifts in accordance with Venus's rotation, confirming the measurements obtained from tracking Meade and other features. The statistical distribution of rotation periods across the solar system highlights Venus's extreme nature. Mercury rotates once every 58.65 days. Earth rotates once every 23.934 hours. Mars rotates once every 24.623 hours. Jupiter rotates once every 9.925 hours. Saturn takes 10.656 hours. Uranus requires 17.24 hours. Neptune needs 16.11 hours. Plotting these periods on a logarithmic scale shows most planets cluster near 10 to 24 hours. Venus sits alone at 243 days, more than 200 times slower than any other planet except Mercury. Mercury's rotation results from tidal locking to the Sun. Venus's rotation remains unexplained by tidal effects alone, given its greater distance from the Sun. The statistical outlier status demands an explanation beyond standard formation processes. Comparative analysis with Mercury illuminates how tides affect rotation. Mercury orbits at 0.39 astronomical units from the Sun, where solar tides are about 13 times stronger than at Venus's distance. These powerful tides have slowed Mercury's rotation from its initial formation value to the current 3:2 resonance over billions of years. The resonance is stable because Mercury's orbit is elliptical, with an eccentricity of 0.2056. At perihelion, when Mercury is closest to the Sun at 0.31 astronomical units, tidal forces peak. The resonance ensures Mercury presents the same face to the Sun at alternate perihelion passages, minimizing the tidal dissipation averaged over time. Calculations show Mercury reached this resonant state within the first billion years of solar system history. Venus orbits farther out at 0.72 astronomical units. Solar tides are 7 times weaker. Venus's orbit is nearly circular, with an eccentricity of only 0.0068. No comparable resonance exists. If tides alone determined Venus's rotation, the planet should spin much faster than observed, perhaps completing one rotation every few Earth days rather than 243 days. What makes Venus special extends beyond rotation to its entire geological character. The planet shows no evidence of plate tectonics. Earth's surface consists of rigid plates that move, collide, and subduct, recycling crust into the mantle over hundreds of millions of years. Venus's surface appears to be a single global shell, unbroken by plate boundaries. Without plate tectonics, Venus cannot cool its interior as efficiently as Earth. Heat accumulates in the mantle until the crust weakens and catastrophic resurfacing occurs. Evidence suggests the entire surface was renewed approximately 500 million years ago in a global volcanic episode that covered the planet with fresh lava. The relative paucity of impact craters, about 900 craters visible across the entire surface, indicates this young age. At current impact rates in the inner solar system, Venus should accumulate roughly 100 craters per 100 million years. The observed crater count matches an age of 500 million years. Recent discoveries about Venus's rotation variations have revealed correlations with atmospheric phenomena that were not apparent in earlier data. A paper published in Nature Astronomy in 2021 by Takeshi Imamura and colleagues at the Japan Aerospace Exploration Agency analyzed cloud tracking data from the Akatsuki spacecraft. Akatsuki entered orbit around Venus in 2015 after a failed insertion attempt 5 years earlier. The spacecraft carries cameras that image Venus's clouds at ultraviolet and infrared wavelengths, tracking cloud motions to measure wind speeds. The data showed that Venus's super-rotating atmosphere exhibits variations on multiple timescales. Wind speeds fluctuate by 10 to 20 meters per second over days to weeks. Longer period variations of 30 to 40 meters per second occur over months to years. These atmospheric changes correlate with the rotation period variations measured by radar. When cloud-level winds accelerate, the planet's rotation slows by several minutes. When winds decelerate, rotation speeds up. The correlation implies a causal connection. Angular momentum transfers between the atmosphere and solid planet must occur through some mechanism. The leading hypothesis involves mountain torques. Venus's atmosphere at cloud level rotates 60 times faster than the surface. Air masses moving at 350 kilometers per hour encounter mountains rising several kilometers high. The mountains deflect the airflow, creating pressure differences. Higher pressure on the western slopes of mountains, lower pressure on eastern slopes generates a net torque on the solid planet. If atmospheric winds speed up, the torque increases, transferring more angular momentum from the atmosphere to the solid planet, and slowing the atmosphere while accelerating the planet's rotation. The numbers work. Venus's atmosphere contains enough angular momentum that transferring a few percent to or from the solid body changes the rotation period by the observed several minutes. But the details of how the transfer occurs, which mountains contribute most, and why the variations occur on the observed timescales remain incompletely understood. Similar phenomena occur on Earth but are much less pronounced because Earth rotates rapidly. Earth's atmosphere exchanges angular momentum with the solid planet through mountain torques, pressure forces over land masses, and friction at the surface. During El Niño events, when the Pacific Ocean warms and atmospheric circulation patterns shift, Earth's rotation slows by about 0.6 milliseconds. The atmosphere gains angular momentum. The solid Earth loses it. Conservation of total angular momentum requires this exchange. But Earth's rotation period is 24 hours, so a 0.6 millisecond change amounts to only 0.0007%. Venus's several-minute variations in a 243-day period represent 0.3% changes, more than 40 times larger proportionally. The difference arises because Venus's solid body rotates so slowly that the atmosphere contains a much larger fraction of the total system angular momentum. Earth's atmosphere comprises only 0.001% of the planet's rotational angular momentum. Venus's atmosphere amounts to roughly 2%. Small fractional changes in atmospheric angular momentum produce large changes in the solid body's rotation. Statistical analysis of Venus's rotation period measurements reveals structure in the variations that hints at underlying physical mechanisms. A Fourier analysis of the rotation period data from 1996 to 2012 showed peaks in the power spectrum at periods of about 5.6 years and 11.2 years. These periods may correspond to cycles in Venus's atmospheric circulation, although the dataset is too short to confirm long period cycles definitively. The 5.6-year period intriguingly matches half the interval between successive inferior conjunctions of Venus and Earth when the planets align on the same side of the Sun. This conjunction occurs approximately every 1.6 years. After 3 or 4 conjunctions, the alignment pattern repeats. If Earth's gravitational influence on Venus's atmosphere plays a role in modulating atmospheric circulation, a 5 to 6 year period might result. The hypothesis remains speculative, requiring decades more data to test rigorously. Unexplained aspects of Venus's rotation continue to puzzle researchers. The exact value of the rotation period, 243.025 days, does not correspond to any obvious resonance or dynamical significance. Some scientists have proposed the period represents an equilibrium between atmospheric thermal tides driving retrograde rotation and solar solid body tides that would slow retrograde rotation and eventually reverse it back to prograde. The balance point depends on the strength of atmospheric tides, determined by solar heating and atmospheric mass, and the strength of solid body tides, determined by Venus's internal structure and the tidal quality factor. Different assumptions about these parameters predict equilibrium rotation periods ranging from 100 to 500 days. The observed period falls within this range, but does not uniquely constrain the parameters. Without independent measurements of the tidal quality factor from seismic data, the equilibrium hypothesis cannot be definitively tested. Ongoing research missions promise to address some of these mysteries. NASA's Deep Atmosphere Venus. Investigation of noble gases, chemistry and imaging, known as Da Vinci, is scheduled to launch in the late 2020s. The mission includes a probe that will descend through Venus's atmosphere, measuring composition, temperature, pressure, and wind speeds at multiple altitudes. As the probe descends over approximately 1 hour, it will experience winds varying from hundreds of meters per second at cloud level to near calm at the surface. Tracking the probe's trajectory using radio signals will map the vertical wind profile with precision unmatched by any previous mission. These measurements will quantify how angular momentum is distributed through Venus's atmosphere and how much is available for exchange with the solid planet. India's Shukrayan mission, planned for launch in the mid-2020s, will study Venus's atmosphere and surface from orbit. The mission carries a synthetic aperture radar for surface mapping and spectrometers for atmospheric composition analysis. Japan's plans for a follow-on mission to Akatsuki would deploy multiple atmospheric balloons to measure winds, temperature, and chemistry at cloud level over extended periods. These balloons would drift with the super-rotating winds, completing circuits around Venus every 4 days. Tracking their positions precisely would reveal small-scale structures in the wind field that might drive the longer-term variations in rotation period. Russia has announced plans for Venera D, a comprehensive mission including an orbiter, lander, and potentially balloons, though the launch date remains uncertain. The case of Venus illustrates how a planet's rotation connects to virtually every aspect of its nature. The slow backward spin influences atmospheric dynamics, magnetic field generation, tidal evolution, and possibly even the planet's volcanic history. Understanding why Venus rotates this way requires integrating geology, atmospheric science, orbital dynamics, and planetary formation theory. The rotation is not an isolated fact. It is the signature of processes operating over billions of years, from the violent impacts that shaped the early solar system to the subtle atmospheric tides acting today. Each measurement of Venus's rotation period, each tracked crater or mountain peak, adds another constraint that models must satisfy. The complete story remains elusive. Partly because of how we because of how we observe Venus, and partly because of what we choose to look for. Our measurements of Venus's rotation carry built-in biases determined by Earth's position in space and the technology we deploy. We observe Venus from Earth, separated by distances ranging from 40 million kilometers at inferior conjunction to 260 million kilometers at superior conjunction when Venus passes behind the Sun from our perspective. This changing geometry means Venus presents different faces to Earth over time, but not uniformly. The near resonance between Venus's solar day and Earth's orbit creates a peculiar selection effect. Every time Venus and Earth reach inferior conjunction, Venus shows nearly the same face toward Earth. Over 8 Earth years, Venus completes almost exactly 5 solar days and returns to within a few degrees of the same orientation. This coincidence means radar observations from Earth preferentially map certain longitudes on Venus, while other longitudes are seen less frequently. The bias affects our crater catalogue. Scientists have identified roughly 900 impact craters on Venus from Magellan radar data, which mapped nearly the entire surface. But ground-based radar observations, which provide the long baseline needed to measure rotation variations, concentrate on the hemisphere that faces Earth at inferior conjunction. This hemisphere includes specific regions near 0 degrees longitude and near 180 degrees longitude. Craters and mountains in these regions have been observed repeatedly over decades, providing the most accurate position measurements. Features at other longitudes, seen less frequently or at unfavorable viewing angles, contribute less to the rotation solution. If Venus's rotation were not stable, if different regions rotated at different rates, our measurements might miss the variation because we observe some regions much more thoroughly than others. How Earth's perspective affects measurements becomes apparent when considering Venus's orbital motion. Venus orbits the Sun faster than Earth, with an orbital velocity of 35 kilometers per second compared to Earth's 30 kilometers per second. During the months when Venus is visible in Earth's sky, the planet moves through a large arc of its orbit. Radar observations must account for Venus's changing distance, its radial velocity toward or away from Earth, and the viewing angle. These geometric corrections introduce small, systematic errors that accumulate over decades of observations. Different research teams use slightly different models for Venus's orbit and rotation, leading to small discrepancies in published rotation periods. The variations are only fractions of a second, far smaller than the real rotation period variations of several minutes, but they complicate efforts to detect very small effects or long-period trends. The bubble concept applies to Venus in a different sense than to cosmic voids. Earth and Venus orbit within a region of the solar system where conditions are relatively uniform. The solar radiation intensity varies smoothly with distance. The density of interplanetary dust and gas is low everywhere. No sharp boundaries separate Earth's environment from Venus's. Yet Venus and Earth evolved along dramatically different paths, despite their similar masses, sizes, and initial compositions. This divergence suggests small differences in initial conditions, possibly including rotation rate and direction, can have enormous consequences for planetary evolution. If we observe the solar system from outside, Venus's retrograde rotation might seem insignificant, a minor peculiarity. But from Venus's perspective, the backwards rotation changed everything. The planet lost its magnetic field, allowing atmospheric loss. It lost its water, triggering a runaway greenhouse. It became hell. The local effect of rotation direction overwhelmed the global effect of orbital position in determining Venus's fate. The typicality versus specialness debate centers on whether Venus's state is rare or common among planets. Based on our solar system alone, retrograde rotation appears rare. 1 planet out of 8 rotates backwards. But this sample size is too small to draw statistical conclusions. The solar system's architecture may not be typical. Perhaps most planetary systems form with multiple retrograde rotators. Or perhaps retrograde rotation is even rarer than 1 in 8, and we happen to observe the unusual case. Until we can measure the rotation of many terrestrial exoplanets orbiting other stars, we cannot answer this question definitively. Current exoplanet detection methods, which rely on transits or radial velocity measurements, generally cannot determine planetary rotation. The rotation axis orientation and period remain unmeasured for nearly all exoplanets. Venus could represent a common outcome or a freak occurrence. We simply do not know. Cosmological principles are not directly at stake in Venus's rotation, but philosophical principles about planetary formation certainly are. The nebula hypothesis, first proposed by Immanuel Kant in 1755 and refined by Pierre-Simon Laplace in 1796, posits that the solar system formed from a rotating disk of gas and dust. The disk's rotation determined the orbital direction of planets and, by extension, their rotation directions. All planets should rotate prograde. Venus violates this expectation. For 2 centuries, astronomers assumed Venus rotated prograde like other planets, despite ambiguous observations. The discovery of retrograde rotation in the early 1960s forced a revision of formation theory. Giant impacts became recognized as important in shaping final planetary properties. The new paradigm holds that initial formation conditions set rough parameters, but subsequent collisions can dramatically alter outcomes. Venus exemplifies this principle. Historical context illuminates how scientific understanding evolves. Nicholas Copernicus in 1543 placed the Sun at the center of the solar system and arranged the planets in their correct order by distance. His heliocentric model explained retrograde motion of planets across Earth's sky as a perspective effect caused by Earth overtaking slower outer planets or being overtaken by faster inner planets. The term retrograde refers to this apparent backward motion as seen from Earth. Venus's retrograde rotation is a different phenomenon entirely. The planet itself spins backwards on its axis, yet the terminology creates confusion. Even professional astronomers occasionally conflate retrograde orbital motion and retrograde rotation. Copernicus could not have known Venus rotates backwards because telescopes had not been invented. Giovanni Cassini, observing Venus through his telescope 124 years after Copernicus published his work, mistakenly concluded Venus rotated prograde. The error persisted for nearly 3 more centuries until radar astronomy revealed the truth. This history illustrates how preconceptions delay discovery even when the evidence is accessible. Anthropic considerations raise uncomfortable questions about observership and habitability. If Venus had retained prograde rotation after forming, the planet might have generated a magnetic field. With magnetic protection, Venus might have kept its water. With water, Venus might have remained habitable for billions of years. Life might have arisen. Intelligent observers might have evolved. Those observers would ask why their planet rotates the right way, while Earth, which they could observe in their night sky, rotates similarly. The question would seem trivial. Both planets rotate prograde because they formed from the same protoplanetary disk. In our actual universe, Venus rotates retrograde and is lifeless. Earth rotates prograde and hosts us. We observe Venus's backwards rotation and puzzle over it. The anthropic principle suggests we should not be surprised to find ourselves on the planet that avoided the catastrophic impact or tidal reversal that would have prevented habitability. But this observation does not explain why Venus suffered that fate while Earth did not. Both planets orbited in the same chaotic early solar system where giant impacts were common. The question becomes whether observers could arise on slowly rotating retrograde planets. If Venus had maintained its water despite rotating backwards, could life have survived the long day-night cycles? 116.75 Earth days of continuous sunlight, followed by 116.75 days of darkness, creates extreme challenges. Surface water would warm significantly during the day, potentially approaching or exceeding boiling in tropical regions if the atmosphere were thin. Night-side temperatures would plummet. A thick atmosphere like Venus's actual atmosphere, but without the runaway greenhouse, might moderate these extremes sufficiently. Life in the oceans would be buffered from surface temperature swings. Photosynthetic organisms would need to store energy during the long day to survive the long night, but algae and cyanobacteria on Earth already possess mechanisms to survive extended dark periods. Intelligent life might adapt to the slow day-night cycle by migrating, hibernating during day or night, or developing technology. The backwards rotation itself, the westward sunrise, would be obvious to any observer with eyes and a sense of time. They would know their world was different. Future surveys of exoplanetary systems will eventually measure rotation rates for terrestrial planets. The technique requires resolving the planet as an extended object, not just detecting it as a point of light. Direct imaging of exoplanets has been achieved for a handful of young giant planets orbiting far from their stars. These planets are hot enough to glow in the infrared and separated enough from their stars to be distinguished with adaptive optics or coronagraphs. Observing variations in brightness as the planet rotates reveals the rotation period. For terrestrial planets like Venus orbiting inhabitable zones, direct imaging requires next-generation space telescopes with apertures of 10 meters or more and starlight suppression factors exceeding 1 billion. NASA's proposed Habitable Worlds Observatory and ESA's LIFE mission aim to achieve these capabilities in the 2040s or beyond. When these telescopes operate, they will measure rotation periods for dozens of Earth-like exoplanets. The statistical distribution will reveal whether Venus-like slow retrograde rotation is common or rare. Venus serves as a natural laboratory for studying atmospheric dynamics on slowly rotating planets. No other terrestrial planet in the solar system exhibits comparable superrotation. Titan, Saturn's largest moon, has a thick nitrogen atmosphere that superrotates. But Titan is tidally locked to Saturn and much smaller than Venus. Venus provides the only accessible example of superrotation on a slowly rotating terrestrial world. Understanding the mechanism that drives Venus's superrotation informs models of exoplanet atmospheres. Many discovered exoplanets orbit so close to their stars that tidal locking is expected. These planets rotate once per orbit, showing permanent day and night hemispheres. Atmospheric circulation on tidally locked planets would transport heat from the day side to the night side. Models predict jet streams and superrotation might develop. Venus tests these models. If we cannot explain Venus's superrotation correctly despite decades of observations, our confidence in predicting exoplanet atmospheres should be limited. The rotation variations discovered by tracking Venus over decades demonstrate that planets are dynamic systems, even on human timescales. Researchers in the early 20th century assumed planetary rotation rates were essentially constant, changing only over millions or billions of years through tidal friction. The discovery that Venus's rotation varies by minutes over years overturned this assumption for slow rotators. Jupiter's rotation period varies by milliseconds due to atmospheric dynamics. Saturn shows similar variations. Even Earth's rotation changes measurably over years due to atmospheric, oceanic, and core dynamics. Planets are not rigid bodies spinning unchanging through space. They are fluid, deformable objects whose motions reflect complex interactions between solid and fluid layers. Venus, with its massive atmosphere weakly coupled to a slowly rotating solid body, exhibits these interactions more dramatically than any other terrestrial planet. The philosophical question of whether Venus's retrograde rotation is special or typical connects to broader questions about physical law and contingency. Some properties of the universe appear fine-tuned, requiring precise values for fundamental constants to allow complexity and life. Other properties seem arbitrary, accidents of initial conditions that could have been different without violating any physical law. Planetary rotation falls into the second category. No law of physics requires Venus to rotate backwards. The rotation could have been prograde if the planet's formation history had unfolded differently. Yet the rotation profoundly influenced Venus's subsequent evolution, determining whether the planet remained habitable. This suggests even arbitrary initial conditions can have decisive consequences. The universe we observe reflects not only the laws of physics, but also the specific sequence of events that occurred as those laws played out. Venus's rotation is one such event, shaping an entire world through a directionality that physics permitted but did not require. The observational program tracking Venus's rotation continues today with no end in sight. Every few years, when Venus passes through inferior conjunction, radar telescopes turn towards the planet and measure the positions of Meade Crater, Maxwell Montes, and dozens of other landmarks. Venus today rotates once every 243 days. Tidal forces from the Sun are gradually slowing this retrograde rotation, working to bring Venus to a halt and eventually reverse it back to prograde. The timescale for this process depends on Venus's tidal quality factor, which remains uncertain. Conservative estimates suggest Venus's retrograde rotation will slow by perhaps 10 to 20% over the next billion years. More optimistic estimates allowing stronger tidal dissipation predict the rotation might slow by 50% or more. But even the fastest tidal evolution scenarios require billions of years to halt Venus's rotation completely. The planet will spin backwards throughout the remaining lifetime of the Sun as we know it. The Sun itself evolves on a timescale that determines Venus's ultimate fate. Our star is currently 4.6 billion years old, roughly halfway through its main sequence lifetime. For the next 5 billion years, the Sun will continue fusing hydrogen into helium in its core, gradually growing brighter. The Sun's luminosity increases by approximately 1% every 100 million years. This seems small, but over billions of years, the accumulated brightening is substantial. 1 billion years from now, the Sun will be 10% brighter than today. 2 billion years from now, 20% brighter. By the time the Sun exhausts its core hydrogen supply in approximately 5 billion years, it will be twice as luminous as the current Sun. Venus currently receives 1.9 times Earth's solar flux. As the Sun brightens, Venus's surface temperature will rise. The planet is already hellishly hot at 735 Kelvin. Increasing the solar input by 10% raises the equilibrium temperature by only about 2%, or 15 Kelvin, because radiative cooling scales with the fourth power of temperature. Venus's thick atmosphere maintains surface temperatures far above what a bare rock would reach through the greenhouse effect. Additional solar heating would increase atmospheric dynamics, potentially strengthening the super-rotation. But the surface temperature rise would be modest, from 462 degrees Celsius to perhaps 480 degrees. The planet remains uninhabitable regardless. Increasing solar luminosity makes Venus incrementally more hellish, but does not fundamentally change its character. Earth faces a different future. Our planet currently sits comfortably within the habitable zone, but as the Sun brightens, Earth will warm. Models predict that in approximately 1 billion years, increased solar radiation will evaporate Earth's oceans. Water vapor in the atmosphere will create a runaway greenhouse effect, similar to what occurred on Venus billions of years ago. Earth's surface temperature will soar above the boiling point of water. the hydrogen from dissociated water molecules will escape to space. Earth will become a second Venus, desiccated and lifeless. Some models suggest cloud feedbacks or other stabilizing mechanisms might delay this fate by several 100 million years, but the eventual outcome appears inevitable unless intelligent life intervenes technologically. Venus's current state foreshadows Earth's future. By the time the Sun exhausts its core hydrogen approximately 5 billion years from now, both Venus and Earth will be sterile desert worlds. The Sun will then leave the main sequence and begin its transformation into a red giant. Over the next few 100 million years, the Sun will expand dramatically as it fuses hydrogen in a shell surrounding an inert helium core. The Sun's radius will grow to encompass Mercury's orbit. Mercury will be consumed, vaporized, and mixed into the outer layers of the red giant Sun. Venus and Earth will survive, but barely. The Sun's photosphere may reach or exceed Venus's orbital radius of 0.72 astronomical units. Even if Venus avoids being engulfed, the planet will orbit within the extended outer atmosphere of the red giant Sun, experiencing extreme heating and drag forces. During the red giant phase, Venus's surface temperature will rise to thousands of Kelvin. The atmosphere will be blasted away by intense radiation and the Sun's extended corona. The rocky surface will melt, creating a global magma ocean. Venus's slow retrograde rotation, if it survives to this epoch, will become irrelevant as the planet transforms into a molten ball orbiting within a stellar atmosphere. Eventually, after approximately 100 million years as a red giant, the Sun will shed its outer layers in a planetary nebula. The core will contract to form a white dwarf, a dense stellar remnant about the size of Earth but with mass comparable to the Sun. The white dwarf will cool slowly over billions of years, eventually fading to a black dwarf. Venus's ultimate fate depends on whether the planet survives the red giant phase intact. If the Sun's expansion envelops Venus, the planet will spiral inward due to atmospheric drag and be destroyed. Computer simulations of stellar evolution show this outcome is possible, but not certain. The Sun's maximum radius during the red giant phase is predicted to reach approximately 1.2 astronomical units, well beyond Venus's current orbit. But the Sun will also lose mass through stellar winds. As the Sun's mass decreases, planetary orbits expand. Venus might migrate outward to perhaps 1.0 astronomical units, potentially avoiding engulfment. The calculations are sensitive to uncertain parameters like the Sun's mass loss rate and the strength of tidal forces during the red giant phase. If Venus survives, it will orbit the white dwarf Sun at a distance of roughly 1 astronomical unit. The white dwarf will emit only a tiny fraction of the current Sun's energy, perhaps 1/10,000th as much. Venus's surface will cool rapidly. Within 1 million years, the surface temperature will drop below the melting point of rock. Venus will solidify once again into a frozen world orbiting a dying star. Any atmosphere stripped during the red giant phase will not regenerate. The planet will become a bare rock, airless and lifeless, slowly radiating away residual heat into the cosmic void. Its rotation, if it still spins at all, will be a relic of processes that occurred billions of years earlier. This distant future holds no place for life or civilization as we know it. Long before the Sun becomes a red giant, Earth will have lost its habitability. Humanity, if we survive, will need to migrate beyond Earth to orbital habitats, Mars, the outer solar system moons, or interstellar space. Venus offers no refuge. The planet's environment is hostile now, and will grow more hostile as the Sun evolves. No technology we can currently envision could terraform Venus into a habitable world. The planet's slow retrograde rotation, which contributed to its loss of magnetic field and water billions of years ago, permanently sealed Venus's fate as an unsuitable home for life. Other observers elsewhere in the galaxy will study their own planetary systems and ask similar questions. If intelligent civilizations arise on planets orbiting other stars, they will observe their neighboring worlds and wonder about their rotations. Some will find retrograde rotators in their systems. They will face the same puzzles we face about Venus. Did a giant impact reverse the rotation, or did atmospheric tides accomplish the feat? How common are backward spinning planets? Does rotation direction affect habitability? These questions transcend our specific planetary system. They represent universal puzzles that any scientifically curious civilization would confront. The answers matter because they reveal how planetary systems form and evolve, which environments support life, and which worlds remain forever barren. Meta-questions about knowledge emerge when we contemplate what we can and cannot know about Venus's history. We observe the planet's current state: backwards rotation, slow period, young surface, massive atmosphere, extreme temperature, absent magnetic field. From these observations, we construct narratives about the past. We simulate giant impacts and tidal evolution. We calculate expected outcomes and compare them to measurements. But we cannot directly observe the events that occurred 4 billion years ago. The collision, if it happened, left no survivors to record it. Venus's interior has mixed and equilibrated over billions of years, erasing impact signatures. We are left with circumstantial evidence, models, and probabilities. The truth about Venus's rotation may remain forever uncertain. This is not a failure of science, but a limitation of historical investigation. We can understand the physical laws that governed Venus's evolution. We can predict what should have happened under different scenarios. But determining which scenario actually occurred requires evidence that time has destroyed. Philosophical synthesis brings us back to the fundamental strangeness of Venus. Time does not literally run backwards on Venus, despite the provocative framing. The planet obeys the same laws of physics as every other object in the universe. Entropy increases. Cause precedes effect. The arrow of time points forward. What runs backwards is the rotation. The sun rises in the west and sets in the east. This is a geometric consequence of retrograde spin, not a violation of thermodynamics or causality. Yet the metaphor captures something true about Venus. The planet developed along a path opposite to expectation. Where other worlds rotate in the same direction they orbit, Venus spins against its motion. Where fast rotation might have preserved habitability, slow backwards rotation contributed to Venus's transformation into hell. The planet's history is one of reversal, of expectations violated, of normalcy inverted. The opening observation that Venus's day exceeds its year still startles despite our intellectual understanding. 243 days to complete one rotation. 225 days to orbit the sun. The numbers seem wrong because they violate our terrestrial intuition. On Earth, the day is much shorter than the year. We measure years in hundreds of days. Venus measures days in fractions of years. This inversion stems directly from the slow retrograde rotation. A faster rotation, even if still retrograde, would produce a more familiar relationship between day and year. A rotation period of 50 days retrograde would give a solar day of about 62 days and maintain the expected pattern where years exceed days. Only Venus's extremely slow rotation creates the paradox where the planet completes its orbit before finishing one spin. Standing on Venus's surface, if such a thing were possible, the sun would move so slowly across the sky that its motion would be imperceptible over hours. You could watch the sun for an entire Earth day and detect no change in position. Only over weeks would the sun noticeably shift westward, climbing from the western horizon towards zenith. At Venus's equator, the sun takes 29 Earth days to travel from horizon to zenith, another 29 days to descend from zenith to the opposite horizon. The experience would be profoundly disorienting. Our biology evolved under Earth's 24-hour day-night cycle. Circadian rhythms, sleep patterns, metabolic processes all synchronize to this timescale. On Venus, with its 116-day solar day, those rhythms would be meaningless. Life as we know it could not function. Venus's backwards time is incompatible with life. Yet in the cosmic scope, Venus's rotation is unremarkable. The planet obeys Newtonian mechanics and conservation laws. It occupies its orbital position in accordance with Kepler's laws and gravitational physics. That it spins backwards rather than forwards changes nothing fundamental about its existence as a planet. The universe does not care about rotation direction. Physics permits both options. Venus chose, or was forced into, the backwards option through the contingent historical events that shaped its formation. The rotation direction matters enormously for Venus's climate, magnetic field, and habitability. But it matters only because of how rotation couples to other physical processes, not because retrograde rotation violates any cosmic principle. The lesson Venus teaches is that details matter. Small differences in initial conditions or chance events like giant impacts can determine whether a world remains habitable or becomes lifeless. Venus and Earth, similar in size and composition, orbiting adjacent positions in the solar system, evolved along divergent paths. One path led to oceans, life, and eventually intelligence. The other led to a runaway greenhouse, atmospheric loss, and perpetual sterility. The fork in the path may have been the retrograde rotation, or it may have been orbital distance, or atmospheric composition, or the timing of water delivery, or pure chance. We cannot rerun the experiment. We observe the outcome and work backwards, seeking causes in the distant past. If this journey through Venus's backwards rotations spoke to you, consider subscribing to continue exploring cosmic mysteries that help you drift into sleep. There are more strange worlds waiting, more impossible physics to contemplate, more questions about existence that dissolve gently into dreams. Leave a like if you found peace in Venus's slow westward sunrise, in the patient turning of a world where days outlast years. And good night, wherever you are in this vast, strange universe where even time can seem to flow backwards if you look from the right perspective, on the right planet, under the right alien sky.